Okay, we see your screen. Okay, great. Perfect. So, okay, that's great. Okay, so we see very well the okay, that's fine, and the presentation as well. So it's okay. So then there are two missed. So I give the floor back to Emanuele. Otherwise, we are waiting for Monsieur Demon 2 and Wojciech Matsevski, not yet arrived. So it's, I think for the moment it's fine. So I think there is no problem with connection. So it's supposed to start at 2 o'clock with the NASA intervention.
So just to remind me, we have to warn presenters when they have only 2 minutes left, right?
Yeah, according to what I've been told, yes.
Okay, so we have just to say 2 more minutes.
Yeah, I think
yes,
so.
Leila, something like this. Thank you.
Okay, there
And
is
I
no
will
ring.
give the right to present from one presenter to the other.
Sounds ringing, something like this is at the end is quite annoying. So it's better if the chair interrupt for a while, just to say 2 minutes left or something like this.
Okay,
thank you.
As soon as you start to introduce the new presenter, I give him or her the floor to the right of presenting. So there is no problem of delay of timing of screen sharing.
Okay, fine, thank you. Oh, there is a message from Cristina Vitucci.
Yes.
I don't know why. Now my button share is not habilitated.
No, because only the presenter can do this.
Okay.
So I moved the rights from one presenter to the other.
So now it's
yeah, that's a nice. You're not anymore able to share the screen because you're not the next presenter. Let's say.
Okay. Thank you.
Welcome.
There is a small green ball that will be moved from a presenter to another. If you have the ball, you can share the screen. Basically, the concept is this.
Okay. There is a message from Simonetta Paloccia.
Yeah, she's trying to to speak, but no.
Simonetta, you had the same problem during the Permanent Steering Committee meeting.
Because your microphone seems open.
Yeah. Looks like.
Yeah.
The keynote is in this same room, right?
Eccoci.
Oh,
Sì, ok, tutto bene.
Ciao Simonetta.
Sì, sentiamo.
No. Perché tutte le volte non so perché, ma mi ricambia il settaggio e quindi tutte le volte mi tocca riprovare. Poi faccio il test e funziona anche in quell'altra maniera, ma evidentemente non è. Va bene, basta, mi rimuto subito. Si prova a fare un sharing del mio video? Perché introdurrò io il Golden Florin.
Va bene. Okay. We have lost Giuliano. But I think I can. Okay.
Sì, I give her the right of sharing.
Your video, Giuliano, was stopped for a while. And a warning of low bandwidth appeared just for a while.
Strange, because I'm cabled with.
You are directly connected to the fiber in person.
More or less.
Allora,
wired.
vedete
Sì,
il
si
mio
vede, si vede.
schermo?
It's okay. We can see the presentation.
Perfetto, basta che mi avvertiate, poi io vado
Puoi
via.
mettere in modalità tutto schermo per essere sicuri, giusto per check. Perfetto, grazie.
Ok, grazie a voi.
Ok, so I give back.
Ora mi muto e vado via.
Okay.
Stop sharing. Ok.
Vai, Manuele, ti do i diritti se vuoi mettere quella presentazione, quella slide di prima. Se, come te.
We are still missing
to miss
William
e
Blackwell
Marzewski.
and also William Blackwell.
Yeah, Blackwell of NASA.
I'm a bit worried about it because we should start in
10 minutes. I know.
And
let's say 12 to be optimistic.
You will come. You come. US, real time, just in time delivery. Okay, just a short question to Leila. So we do as we talked. So that I will start the first 4, and you will continue with the last 4, right?
Yes, sorry, I forgot to tell Emanuele and Giuliano.
Okay.
Yes, Thomas will be the first chairman, and then for the first 4 presenters, and then I will take the chair.
So up to Samuel Fabrichon will be Thomas, and then till the end will be Leila.
Okay.
Indeed, the reason is I'm presenting in the second half. It's stupid to introduce yourself, so so it's better to like this.
Okay. We will also try to report on the WebEx chat any question from the YouTube chat. So have a look from time to time to the chat. In any case, we will try to support you with this because it's not completely straightforward. Also because YouTube has some delay. So possibly in some cases we are able to switch the question is too late when we can forward the question. So it's not so straightforward. But
okay, thank you for your assistance.
Thank you to you, Leila, for chairing the session. But
I think it's harder for you, Giuliano and Emanuele. But in the end, we just have to say the names of the presenters.
We have been trained for this.
Oh, okay.
We are one team. Like, we will find it out.
okay. In the meantime, I can set up again the background and
there you go. Mr. François de Montou.
Okay.
May I ask you to test if the audio is okay? And well, welcome first of all.
Yeah, welcome.
Bienvenue.
Hello.
And then if I can ask you to share your screen with presentation, just to double check everything's okay.
Okay.
You should have received the right to present. Perfect. Yeah, that's fine. And then, yeah, that's perfect. Thank you so much. And then there is Mr. Marzeski not yet arrived. Okay, I will check. Give back to the presentation to Emanuele. Okay.
So, Giuliano,
Yeah.
there is anyone missing now?
Yeah,
Apart
there is Mr.
Blackwell.
Martsevsky. I don't know if it's just right. No, Martsevsky, and Mr. Blackwell from
Yeah. I'm really worried about it.
It's quite early in the morning, I think, in the US.
Yes, yes.
I don't know in which part he's presenting from, but in which area, but it can be really, really early in the morning.
It's even earlier in the West Coast.
Oh, okay. In the West Coast, wow.
The West Coast is even earlier.
So just awakened, probably.
Yeah, possibly is just sleeping and we are trying to contact him by email now.
Okay.
I hope we will be able to start in time.
Mm.
This is quite unfortunate.
Yeah, because Mr. Martseski anyway is going to present at the 3:45, so we have quite time. Even if it's arrived a bit late,
Yeah.
it's
maybe also not everybody understands to be here even before the keynote is something that they can also start with the keynote, but there's time.
We attempted to spread this information, but possibly someone did not understand well. But the keynote presenter should be there at the time of the keynote.
True.
But only one is missing, so...
Only one for the moment. Well, the first one is the Tordinesa keynote.
Okay. Yes. This is because I was saying that the which is about
the session one.
Yeah, for session.
For session one, only the sixth presenter by
yes, the
Martseski.
sixth. So not bad, but
no.
The keynote presenter.
This is the.
Oh yes, Huilu is saying the VIP is missing. Yes, right.
Very important presenter.
But you know, the VIPs always come last. Maybe you know it's a last.
Yes, but usually the women come last.
We are trying to reach Blackwell by email, but for the moment we didn't get any reply. No. So I would suggest to wait more, few minutes more, and let's see. I don't know.
Avete provato a mandargli un'email, un messaggio?
È quello che ho detto adesso, Simonetta. L'ho appena detto. Per ora non ci ha risposto.
Hello.
Hi, Mr. Blackwell.
Hey, can you hear me?
Yeah, sure. I will give you the right of presenter as well, so you can share your screen.
Thank you. I am terribly sorry about the difficulties. My network connection went out right before the session. So let me get started here. Should I just go ahead and start?
Yeah, I think so. I don't know if Emanuele or the say of that representative want to say something, but I think that it's first it's the NASA. So it's I think you can. I mean, you can speak. You can start presentation. I think.
Yes, very good. All right. Thank you very much. Again, my apologies. So I wanted to talk about small satellites and constellations as they are now applying to the NASA portfolio. My connection to NASA is that I am the PI of the Tropics constellation mission. And one of the things that we've seen here at the conference and for a while now is that CubeSats and small sats are becoming more pervasive, certainly in the technology portfolio of NASA, but also now more in the science portfolio. You're seeing CubeSats and small sat constellations start to take on science missions as the primary observatories. And two examples of that. So the Cygnus mission, this is the mission Chris Ruff is leading to do ocean surface winds and soil moisture. It's got 8 small satellites, has been operating very nicely and continues to provide great data. So that's a good existence proof of what these missions can do. More recently, there's a pre-fire mission. That's a long-wave infrared constellation of 2 6U CubeSats that will be launching here in a number of years. So you're starting to see more and more in Earth science and even space science for NASA, small satellites taking on more of the science role. So what I wanted to do in this talk against that backdrop was provide some examples from Tropics of how we've been able to advance some of the instrumentation and take advantage of these rapidly evolving capabilities for smaller satellites and ground stations and mission operations and processing and so forth to realize some of these new missions. And my focus here is going to be on atmospheric sounding and precipitation monitoring. So there's a whole host of things that you might think about constellations to take on, but I'm going to focus on these particular missions. And just to start with a very broad brush, I think one thing that, of course, is driving this is technology continues to evolve in multiple dimensions. So just a couple of examples here on the screen in terms of computing power, just the sheer number of capability per unit cost, per volume, per mass, continues to increase rapidly. Right? So we've got more computing power on our iPhones than we could ever dream about 30 years ago. We're making smaller mechanisms that can, for attitude control and for pointing and things, much more capable than we had decades ago, and even launch. So here's an enabler for constellation where we can now launch smaller payloads for single-digit millions of dollars. Number one, and number two, we're starting to see things like orbital transfer vehicles that can drop off small satellites at precise spots in the orbit to fill out a constellation. So taken together, these and many other things really enable new architectural tools to think about in the context of small sats and constellations. So how does that impact Earth observing satellite? There's a lot that we can think about in terms of architecting future missions to exploit these with a focus on the smaller satellites and constellations and how we can be smarter with architecting the missions. Just to point out that there are a number of good reasons why you would not want to consider smaller satellites and CubeSats. Here's just a couple of comments on that. So, you're not going to get around, diffraction limits, right? So if you've got an application where you need very fine spatial resolution, that's very challenging from a small satellite platform, maybe not impossible. There's a lot of work on deployable antennas and so forth, but that's a real challenge. If you need a big aperture on a small satellite, that can be a problem. Of course, power, if you've got a radar or a power-hungry instrument, that's hard to do from a smaller satellite, all things being equal. But again, there are advances in deployable solar panels and more efficient solar cells and so forth. For pointing, they're really nice star trackers. They're small, that you can fly in CubeSats now. So that's changing the game a little bit with respect to how well we can control and point the satellites. One big one is the data quality. Okay, so once you make the observation, you've got to calibrate it, you've got to geolocate it, all the things you traditionally do. So some of the compromises that you have to make for flying on a small satellite might complicate or degrade your ability to do that. So that requires a lot of thought. And finally, reliability. So we're used to these space systems lasting many years, even decades. So you either need to think about how you make the satellite more reliable or architect the constellation in such a way that you have redundancy at the system level and maybe you can live with a low reliability at the spacecraft level. All right, so against that backdrop, here are some things I wanted to go through. So the key part of this talk really is the technology advancements. What's been happening recently that enable us to think about smaller platforms to tackle some really hard Earth science problems. And I'll go through that again through the lens of the TROPICS mission. And then I'll end with just some considerations, things to think about that will help or facilitate the use of smaller satellites for some of these missions. I think it requires a little bit of thinking differently about the problem in terms of breaking it up, maybe disaggregating some of the objectives and so forth. Okay, so there are a number of instruments and measurements that we can make to measure the atmosphere. Again, the focus of this talk is really atmospheric sensing. Here are just a few examples of these things: ground-based radars, aircraft-based measurements, large facility class missions. I'm showing you there. This is the GPM mission here in the middle. Visible high-resolution imagers, radio occultation. These are all great missions. Some of them are more amenable to miniaturization than others, but the sweet spot for the work that I do is really passive microwave sounding. It's a good compromise of the variables that we're trying to measure for severe storms and atmospheric characterization, temperature, moisture, precipitation. You can do that usefully with a passive microwave sounder. It's not the best observation usually for these, but it can penetrate the clouds. The resolution is okay. It's a good all-around compromise for these kinds of measurements. So I'll be talking about passive microwave sounders. So here's a little primer on the atmospheric transmission in the microwave and to point out some of the absorption lines that we use typically. So we have oxygen lines near 60, 50 to 60 gigahertz, 18.75 that we use for temperature profiling, water vapor line at 183, and typically some imaging channels around these absorption lines so we can see the surface. And another thing to point out here is this continuum absorption. As the frequency increases, the transmission decreases by lambda over lambda squared, essentially, right? This is square power. So you've got to deal with this. If you're going to try to observe at higher frequencies, you have to contend with this absorption that's increasing. And of course, the microwaves can penetrate the clouds and see what's happening below the cloud tops, which is a big advantage in atmospheric sensing. For precipitation, especially in the use of millimeter waves, we're looking at emission and scattering from the cloud. So this is just a depiction of this is a lambda to the fourth phenomenon here. We can see a lot of scattering as we go into the sub-millimeter waves, which is good and bad. Okay, so we can get a high resolution picture of the ice scattering in the clouds is a good thing. The bad thing is that we cannot penetrate very low below the cloud top at these higher frequencies. So one thing to think about is how we use a broad set of frequencies to try to derive as much as we can, given the limitations of things like spatial resolution and so forth. Okay, so let's get into some technology advances that we've been working with TROPICS. So there's been an evolution that we've been working for the last decade to try to realize a science class constellation. And here's kind of a thumbnail sketch of how that's gone. So we started working with some university partners on receiver front ends. This is kind of the first thing you think about. You need very small, low power, sensitive, stable, easy to calibrate receivers to fly on these systems. So the key to that really is a high level of integration. You can put more and more functions on a chip now. So we've been working that with the folks at UMass Amherst. We've then started to figure out, how, if you could make a small payload, how would you host that on a very small satellite? And there are all kinds of things to worry about. You've got to move the antenna beam across the Earth as you fly. You've got to keep the spacecraft stable and pointed and geolocated as you do that in a very small platform. So there are a lot of challenges from an aeroastro standpoint to solve there. So we've worked with the folks at MIT campus on those kinds of problems, deployed MicroMass 1, which is the first cross-track scanning radiometer Back in 2015, this mission was mostly successful. We figured out how to do all the spacecraft control and how to build the payload to TRL-6. Murata, we flew in 17, again, partially successful mission, incrementally improving our ability to do these kinds of things with multiple bands. We now have a temperature radiometer and a moisture radiometer. MicroMass 2A in 2018, it all came together, everything worked great, and we proved that we could do this, high fidelity sensing of temperature, moisture, and precipitation in a 3U, this is a 5 kilogram class CubeSat. And so this trajectory is probably consistent with other things that are happening in the community, but this is how it turned out for TROPICS. And just to point out that there are many other missions that you're probably aware of that have done great things and are continuing to do great things in terms of demonstrating capabilities in very small spacecraft. We heard about IceCube, Tempest-D, RainCube. These are 3 NASA technology demonstration missions that have been tremendously successful in demonstrating that we can get very good performance and sustained performance in a very small, affordable platform. So given these existence proofs, there's just a lot of potential in how we can leverage these kinds of instruments for constellations for widespread, high resolution, high revisit rate coverage. So the trick of miniaturizing the radiometer payload for TROPICS really comes down to a high level of integration and a high level of modularity. So I'm showing you here the key pieces of the payload for TROPICS. So we have radiometer front ends for the water vapor and the temperature bands. The temperature receiver spans 90 to 120 gigahertz. It's LO driven. There's a back end filter bank here for that system. There's control and data handling and a motor that turns the payload relative to the bus, and the signals will go back to the bus over a slip ring. There's a very nice antenna that handles the dual band, the 90 to 120 and 180 to 205 through a wire grid dichroic parabolic back end here. And this, we most of the volume for this antenna and tuck the electronics around the sides and the back of this to keep the payload as small as possible while maximizing the size of the aperture for better spatial resolution. Okay, so here is a picture of the finished receiver modules for TROPICS. So this is the UMass Amherst receiver on the left. And these are, on the order of 50 grams, a quarter of a watt power consumed, again, highly integrated, low power electronics. Virginia diodes made our G-band direct detect. So there are 4 channels that come in here, and they are filtered and direct detected all in the block. And then they go back to the spacecraft for control data handling. So very small, low power, sensitive receivers is really one of the keys of this. A few more details on the front ends here. So I mentioned there's a higher level of integration happening now. So there's a silicon germanium chip that we use that has a tripler, down converter, amplifier, all on the same chip. We can get miniaturized COTS, local oscillator parts that are very stable and low power now. And that's really one of the keys, this wealth of commercial parts that are reliable and low power and high performance. And that's really driven a lot by the communications sector. We're backdrafting on a lot of that nice work. So here is more details on the silicon germanium chip. This is the IBM 9HP process, which works very well up into the millimeter wave now. You can put a lot of functionality onto a single, very small circuit board. So you can see we've got the tripler in the front end and the IF back end all in the same chip. So these are the kinds of things that we're leveraging to make these parts smaller while still maintaining performance. On the G-band receiver, again, this is a direct detect part. So we've got some amplification in the front here, power dividers, and then some filtering on the back end before we do some analog signal conditioning. So the challenges with this kind of work has to do with the noise of the front end, and the 1/f, the flicker striping noise is a big concern. So we work very carefully to select parts on the LNAs and the detectors, even the voltage regulators and the op amps all contribute to the 1/f noise. So there's a big system optimization problem to get all that optimized. Another big part of this is calibration. So noise diodes are used in TROPICS. The noise diodes have had a bit of a checkered past. So it's a really difficult thing to get a noise diode to work as a calibration source for a radiometer. You've got electrical design to worry about, mechanical, thermal, and radiometric. And you've got to essentially perfect all four of those simultaneously all the time to get those to work. And on top of that, you've got to worry about reliability. This is your calibration source, but it's got to work throughout the mission. And again, one of the things that's helped us get better at that is this higher level of integration where we can put the diode right on the same module with the receiver. And that actually makes some of those components easier to design. And what I'm showing you on this slide are some results from the GMI sensor. I showed you a picture of this earlier. And GMI for the first time flew together onboard calibration targets and noise diodes up to 37 gigahertz. So we can have a nice opportunity to compare the stability over many years of life. And the noise diode stability is absolutely amazing. I mean, you can see here on this chart, it's in the orders of tens of millikelvin stability over many years of life. So this gives us hope that the noise diodes can be used effectively even as a primary calibration source for these small instruments. And another interesting aspect is the comparison of the calibration targets and the noise diodes. And those of you who've worked on these large microwave systems understand that it's exceedingly hard to keep thermal gradients off the calibration target. We go to great lengths to shield them and shroud them and tuck them away deep in the instrument to keep the sun off. And even after doing that, we still see gradients on the targets. This is a GMI plot, essentially showing the gradient of temperature sensors in the instrument versus gradients through the load. And you can see the gradients on the target are actually quite a bit larger than the numbers I showed you on the last slide here. So there's challenges with the internal calibration target as well. Okay, so just to take you through some of the highlights of the Tropics hardware, the antenna was absolutely fantastic. This was work done by Thomas Keating, and this was very challenging to get this very compact design. We had very stringent requirements on performance, beam width and beam quality. And just to test the side lobe levels of this antenna, challenge what we could do in our antenna range. So we have very nice beam efficiencies. The side lobe very low. Met all our beam width requirements, and we're able to do this over 2 bands and satisfy our thermal and vibration requirements. This was really an engineering triumph on this antenna. Just to point out, our channels on Tropics span 90 to 120 gigahertz. We're trying to keep up temperature, moisture, and imaging. Over 12 channels. Our spatial resolution at Nadir is 24 for the temperature bands and 17 for the water vapor bands. Any delta T's are on the order of a degree for temperature, a little better, and half a degree, 0.6 degree for water vapor. Here are the pictures of the flight hardware, the finished products of what I showed you in the exploded diagram, control data handling, the slip ring and motor assembly, very thin, reliable part here, and all the other radiometer electronics. Here's the integrated payload assembly to show you how this all fits together, the humidity receiver and the temperature receiver, again, tucked on the edges. Here's a pretty good shot of that wire grid diachroic beam splitter and the scanner assembly and slip ring on the bottom here. So another thing that we spent a lot of time and effort on was the TVAC pre-launch calibration on Tropics. To convince ourselves that the radiometer was stable over long time scales, sensitive, linear, and so forth. So we built a custom calibration assembly with multiple calibration targets to assess all these aspects for every satellite. And we got really good results. Vince Leslie will talk more about this in his talk tomorrow. We measured 7 satellites. They're all in family and all meet requirements and perform very well. So we have high hopes for the calibration of Tropics based on these kinds of measurements and other things. So the radiometer, I think, is again, a real engineering achievement in a number of ways in terms of the number of channels packed in a very small package, the spatial resolution we're able to get in a very small package, and the performance in terms of the antenna beam quality, side lobes, resolution radiometrically, and so forth. So we're very proud of how this came out in terms of the testing. And here's the complete space vehicle. So as I mentioned on Monday, we're going to fly this qualification unit next year, and the Constellation will fly in early 2022 with 6 more vehicles that look like this. So just to end up here and wrap it up full circle, So given these new capabilities and these enabling technologies to make new measurements in smaller packages, how do we think differently about architecting missions? And here's one I think is very important, I think if you can find a way to target what it is that you're going after and optimize your observatory around that target observable, it can go a long way. For tropics, we're trying to measure tropical cyclones, and we take advantage of the fact that they are they're not spatially random over the entire globe. They're predominant in these latitude bands plus minus 15 to 20 north south. So we can use that to our advantage when we architect the constellation to put the satellites in just the right orbits, just the right configurations where we have the maximum sensitivity over these latitude bands. So these are the kinds of things that we can do with future constellations. So if you integrate over latitude, here's the curve that you get. These two bands, and by selecting the configuration of the constellation, the inclination of the orbits, the altitudes, the width of the swath, we can actually align our sensitivity to where the tropical cyclones are formed. So these are the kinds of things that we can try to do. So I guess spatial resolution is one big one. How do you overcome challenges for spatial resolution given the constraints on small platforms? And here are a couple of thoughts on that one. And again, I'd like to come back to think big picture at the system level to try to optimize it at the system level rather than at the sensor level. In some cases that will help you, in some cases it won't help you. And here are some obvious things that you might consider. Flying lower gives you better resolution. So if the tropics constellation is going to fly lower than traditional operational polar orbiting satellites for better resolution. If you can move to higher frequency, that offers an advantage from spatial resolution. There are challenges there I pointed out for water vapor continuum and others. Geometric diversity. So if you can observe the atmosphere from different perspectives, different angles, vantage points, that can be exploited and perhaps buy back some of the degradation in spatial resolution. And there are other areas of the trade space that you can try to optimize at the system level, noise, revisit, even spectral resolution, right? So just think of this as a complete system optimization problem, and you'll find that maybe you can mitigate some of these challenges that you think might poke out from a small set constellation perspective. And with that, I'll wrap up. I started late, so I'll leave some time for questions. But the takeaways here are, look, there are a lot of technology advances coming along. How can we be smart about leveraging them for future constellations? Being aware that there is no silver bullet. There are some times where this will work well and sometimes it will not. So I think it's important to understand what the pros and cons of these new classes of observatories will do. And with that, I'll stop. But thanks very much.
Okay, thank you, William. Thank you, and good that you solved your network troubles and you've been able to present. Very interesting. We have a few minutes for a question from the audience, if any.
Good afternoon. Giuseppe Virone, CNR. May I ask a question?
Yes, please.
Thanks for the very good presentation, very amazing presentation. And my question is, after having a quick look at the antenna, I noticed that there are the two bands are working in single polarization. Is it correct?
Correct.
So is there any appetite for having a system in dual pole in the future?
Sure, I think absolutely there is. So for the applications that we have, the information that we get from dual polarization it doesn't add a lot of information, but there are certainly other things where dual polarization is very important with respect to, if you're looking at cloud particle microphysics and certainly surface properties. So there's certainly an interest in that, and there are ways to try to get dual polarization measurements in smaller instruments. But again, that introduces another level of complexity. But there's certainly interest and work in that area, definitely.
Thank you very much. Thank you very much.
Oh, we have a question from YouTube. Just a minute. I am going to forward to the chat. What is the NENR of the noise diodes at the highest frequency band?
Yeah, good question. Excess noise ratio is so we're getting about 15 dB near 200 gigahertz, which is pretty good. And that's Virginia Diodes worked really hard to optimize that over a number of design iterations, and that's come a long way. So, we can use a very weak coupler and still get on the order of 300 Kelvin calibration noise in the front end.
Any other question? We have one from Simone. Simone, you can ask directly by switching on your microphone. I think it's better.
Okay, thanks. Hi, William Blackwell. A very interesting presentation. And my question is, the antenna used for the performance, I think it could be a circular horn. Is it correct? Because it isn't shown in the presentation, the geometry of the antenna.
Yeah, the feed horns are circular scalar feeds.
Okay. Okay, thanks.
Okay. I think it's time to move to the next session. I would warmly thank William for this very interesting presentation, very interesting keynote, and see you. Just let me to recap some very briefly about the program for today, and very, very shortly. Okay, we are at the fourth day of the MicroRad 2020, and from now MicroRad will split into two parallel sessions. The first is land on room 1, and the other is combined ocean, atmosphere, and electromagnetic theory and models in room 2. At 4:30 p.m. Central Europe time, we will have 15 minutes break, shorter than usual. And then we, at 5:15, the Golden Florin or Fiorino d'Oro Award will be held in room 1. And all the participants to MicroRad 2020 are kindly invited to attend. The second part of the parallel session will restart at 5:15. Just let me say that my usual annoying recommendation to presenter and the chairs, please keep the schedule. You are allowed 10 minutes for presentation, 5 minutes for question and answers. I would again remind that all participants connected by WebEx are enabled to mute and unmute their microphone by themselves, so all of you can ask directly to the presenters. And as you have seen, we are also trying to report the question from the YouTube chat. And final recommendation, the presenters for the second session are invited to connect to the pre-session during the break for verifying audio, video, and screen sharing in order to ensure a smooth prosecution of the conference. That's all from my side. Now in room 1, we will have the session land. And I'm going to give the floor to the session chair, Leila and Thomas. Thank you and enjoy MicroRad 2020.
Thanks a lot, Emanuele, for introducing the land session. Now we have 8 talks, and we will split Leila and me. So I will present and introduce the first 4 speakers, and then Leila will introduce the second 4. And I think we just start. As Emanuele said, you will get a little warning from us after 8 minutes that you can finish on time after 10 minutes. And then we will have the question and read them to you. And we will start with the first presenter, which is Ichiro Kaihotsu. And he will talk about evaluation of the MSR2 L2 slow motion product of JAXA on the Mongolian over 7 years from 2012 to 2018. Ichiro, please.
Thank you. Hello, everyone. I am Ichiro Kaihotsu from Hiroshima University. Today, I am going to talk about evaluation of the AMSA2 L2 soil moisture product.
Sorry, Ichiro. Sorry if I interrupt you, but please share the screen. Can you share the screen with the presentation? Yeah, okay.
Is this okay?
Yeah.
Okay. Okay.
Could you use full screen presentation, please?
Yeah. Sorry.
Fine.
Okay. This is an outline. As you know, answer 2 and SMOS have been globally and successfully observing soil moisture since 2012 and 2009 respectively. This is a nice long observation of soil moisture. So it's very important to check the measurement accuracy and the observation quality of both satellites. The purpose of this study to make an evaluation of the AMSA2 L2 soil moisture product using in situ soil moisture measurements at 3 centimeters depth and the meteorological data collected during 2012 and 2018 in the study area on the Mongolia Plateau. And comparing with SMOS L2 soil moisture product in terms of observational stability, measurement accuracy, bias, and effective sampling depth. In order to achieve the purpose, we set the target area M1 in the study area on the Mongolian Plateau. M1 M1 corresponding to 1 pixel size of AMSA2 in the study area. We had in total 7 automatic stations, 2 AWS and 5 ASHs with TDR probes which measure soil moisture at 3 centimeters and 10 centimeters depth in M1. This slide shows time change of soil moisture at 3 centimeters depth of all the stations from 2012 to 2018. We use this data for the evaluation. The mean value of annual area average precipitation in M1 from 2001 to 2017 was 112.8 millimeters per year. So we defined that a year with annual rainfall more than 112.8 millimeters per year was a wet year. In case of less than 112.8 millimeters per year was a dry year. 2013 is the wettest year, and 2015 is the driest year. So basically, I will discuss the study results in 2013 and 2015. This slide shows time change of AMSA2 soil moisture with in situ soil moisture in 2013 and 2015. You can see that the AMSA2 soil moisture responds well to rainfall events and matches mostly with in situ soil moisture in terms of the pattern of change and the magnitude of value. And the response on descending is better than on ascending. Furthermore, I would say that the response in 2015 dry year is better than in 2013 wet year. In this figure, you can see a comparison results of soil moistures of AMSA2 on descending around 3 o'clock with smooth on ascending around 6 o'clock in 2013 and 2015. AMSA2 and smooth respond mostly to rainfall events, and there is a little difference between both satellites. In 2013, smooth responds better to rainfall events than AMSA2. We tried to investigate statistically the measurement accuracy of L2 soil moisture products of AMSA2 and smooth at 3 centimeters depth, as shown in these two figures. We can see that the bias and RMSE vary with year. Let's have a look at the upper figure. The values of bias of AMSA2 and smooth on ascending are mostly negative, except smooth on descending. The negative value, which means the underestimation of soil moisture measurement, especially AMSA2 is relatively remarkable comparison comparing with smooth. This underestimation can be considered to be caused by the soil surface conditions. Concretely, their soil surface wet condition, soil temperature change, and vegetation development. In wet years, the values of AMSA2 are little worse than those in dry years. The values of smooth on descending, on ascending are better than AMSA2, and the values of smooth on descending do not almost change. Let's have a look at the lower figure. The RMSE values of AMSA2 are approximately the same as smooth, except 2015 and 2018. In dry years, the values of RMSE and bias are little smaller than those in wet years, except smooth in 2018. RMSE of AMSA2 is best in 2015 with least rainfall. Smooth is best in 2018 wet year. Abundant rainfall promotes wet condition of thin soil surface layer. So the wet condition could potentially influence AMSA2 measurements of surface soil moisture. However, smooth does not depend remarkably on such rainfall condition because it uses a single lower frequency, 1.4 gigahertz, that can measure deeper soil moisture than AMSA2. I would say that the rainfall amount has an influence on AMSA2 and smooth soil moisture measurement, and especially AMSA2 relatively depends on rainfall condition comparing with smooth. In other words, the 3 centimeters depth of in situ soil moisture measurement can be considered to be not an effective sampling depth for AMSA2. So we try to subtract the temporal mean bias, namely we obtained the value of unbiased RMSE, although there is no remarkable difference between the values of RMSE and unbiased RMSE of smooth. The values of AMSA2 in wet years obviously decreased except 2018. This fact suggests that the AMSA2 soil moisture measurement might depend on rainfall condition. Furthermore, we try to investigate the effects of soil temperature change and vegetation development. As shown in this figure, we obtained no relation of soil moisture soil moisture of AMSA2 and SMOS to inside soil temperature. As to vegetation development, we can see also no influence as shown in the right figure. These facts suggest that the underestimation of AMSA2 is caused by the wet condition of the soil surface. In conclusion, we obtained these results, and we need more adequate data sets of inside soil moisture measurements at ineffective measurement depths and different surface conditions in the future in order to improve the AMSA2 soil moisture measurement and the AMSA3. Thank you very much.
Thank you, Ichiro, for the presentation. Now the floor is open for questions. I look to the chat. There is nothing on the chat. Don't see anything on the live stream on YouTube.
Nothing from YouTube for the moment.
Okay, thank you.
Okay. The last moment. Okay. So then we would move on to the next speaker, which is Hui Lu. And it's perfect. The talk is about long-term and consistent soil moisture product from multi-source passive microwave radiometer measurements. Hui Lu, for yours.
Okay, thank you, Thomas. So this is Hui Lu from Tsinghua University. So I will make an introduction about our progress from produce soil moisture product by combine AMSA-E, AMSA2, and SMAP. So I would like to thank my colleagues. Pan Yao is a postdoc of my group, and JC, and Kenjie, Quinn Yang, and also Michael, and Dan, and Dala from MIT is a kind of a cooperation work. So in today's talk, I will introduce our research in following contents. First of all, for the background, we know soil moisture is a very important essential climate variables. And the long and the spatial temporal consistent soil moisture is very important for climate research, especially when you want to do the trends analysis or variability analysis. You need soil moisture data with reliable quality and consistent one. So our motivation is very simple because currently we can say we have many radiometer or satellite can provide soil moisture product from SMMR to up to SMAP. Inside we know the SMAP and SMOS can provide the L-band observation, but we also have AMSA-E, AMSA2 who can provide the C-band X-band observations. Currently, we have soil moisture product from AMSA-E, AMSA2, just like Professor Kakos introduced. Also, I worked for AMSA-E product when I was a PhD student in University of Tokyo. So yeah, Professor Kakos gave some good memory for my PhD research. I also use the Mongolia site. For AMSA-E, AMSA2, we use C-band, X-band data for retrieve. But we know there have some shortage of this for this long wave, for this short wave high frequency product. We cannot have good soil moisture product for the vegetation coverage for many costs. We also have L-band, but it's mainly from SMOS and SMAP. But the problem of this product is short, especially for SMAP. We think it's have a higher accuracy, but we only can get the data from 2015 up to now. So our research is targeted how to obtain a consistent data set by merging the multi-sources product together, especially merging L-band from SMAP to the C-band X-band to AMSA-E and AMSA2. Then we will try to transfer the merit of L bound to the MSI and MS2. So then we can have our data set start from 2002 up to now. Our method is very simple, and straight away we just want to use the artificial neural network machine learning method and training the MSI and MSI2 observation to the SMAP1, and then can get a long-term so much data. The work content is 3 steps. First one, we should build a Bright's temperature data set. It's continue from MSI to MSI2. But as we know, there's some kind of, gap between MSI and MSI2 from 2011 to 2012. So in our first step, we'll try to build the relationship between MSI2 and MSI. For our current work, we're training the MSI data to the MSI2, and we use the MSI L1S data. This is kind of slow scan data set, but we can use this kind of overlap period and calibrate the MSI data to the MSI2. Because we have MSI2 and SMAP overlapping, so we think currently we calibrate MSI data to MSI2. This is just some kind of result for that kind of MSI calibration. We'll have MSI over the original data like this way for say bound edge polarization. After the calibration to the MSI2, we have this kind of figure, this kind of 0.25 resolution one. Because we want to training our TB according to the SMAP observation, so we should rescale the 0.25 degree data to the 36 kilometer resolution as the SMAP resolution. So we have this kind of calibration and the scale. When we have match the MSI and MSI2 TB, then we can training this TB use SMAP L3P source product. Our input data is just from MSI and MSI2 TB from C band, X band, and also we calculate some index and also use apparent temperature calculated from 36.5 gigahertz and input to the neural network. The training period is from 15 to 2017, 3 years data, and we can train in the data according to the SMAP L3 soil moisture and produce our data set, so-called NN soil moisture. We compare our data to the training the product to the MSI to the SMAP original product. We have very good correlationship and a very small RMC corresponding to the SMAP observation. We can say we have some error in the tropical region because they have a very high vegetation water content, and MSI2 and also SMAP cannot have a good observation. So for another region have very good, very small MSE and a very high correlation coefficient. There are just some animation we have training our MSI and MSI2 TB for each day. So we can have this kind of daily and night observation of the surface soil moisture from our neural network. In the third step, we validate our product use the international soil moisture network data. So we select the network soil moisture data over US, Africa, European, and also Tibet Plateau. Each network have many stations, then we can partly mitigate the scale mismatch problems. First of all, we compare our soil moisture data with the SMAP1. SMAP1 showing the red dot. Our one is showing blue dot, and the observation is the green line. It's clear for the US network, Tibet network, and the European and Africa network. Our product is in a good relationship to the in-situ observation and also have the same accuracy as the SMAP done. Because our product is mainly from AMSA E and AMSA 2. So we compare it to the original AMSA product from JAXA and from LPRM. Our product showing blue dot and AMSA 1 showing green dot and the LPRM showing purple one. It's clear that JAXA 1 have a little dry bulbs and the LPRM one is a little high performance and overestimation. Our one is much closer to the observations. There is another set in the European and Africa case. It's can be sometime working from LPM have very high value and JAXA one very, very low values. This slide shows the static metrics for our product on the different networks. Generally speaking, our product can have a UBMSE around 0.5. It's meet the target of AMSA E product is 0.6. There are some, how to say, advantage or benefit from our product. First of all, it's very easy to compare our product with the SMAP 1. It's just show for the case for the 2018, July 10th. They have two observations, one from SMAP, another one from our product. We can put it together and can easily can find it have a better global coverage and they're very smooth, no any strips. And also we can have a good relationship to show with this kind of dense observation from AMSA product. We can have a daily observation, we can have a good dry down curve and also good response to rainfall. And also we know in 2019 there are some data lost for SMAP, but for this period we can use our product to provide so much observations. And our product can easily move to the AMSA 2, as Professor Kai mentioned, from 2023. So in this talk, I introduce our product. It's based on neural network 1 and merge the SMAP to the AMSA E and AMSA 2, and they show some benefit for good coverage and more frequent observation can be contributed for the land-atmosphere interaction studies. That's all. Thank you.
Thanks a lot, Wilu, for the very nice presentation. So the floor is open for questions. Looking to the chat. Let's see something there. Looking to the YouTube.
No question from YouTube.
Yeah, I have a question. Wilu, I learn about neural networks and this artificial intelligence algorithms any day. So can you specify a bit more how the neural network was designed to do the job? How many hidden layers, or what was exactly, how was this designed? Can you explain it more on this?
Yeah. I don't write here. We have three layer for this network, and I think for this kind of training case, we do not need too much layer and too much nodes. But from my experience, I should say that how to say. It's really interesting. We should input some kind of index. We should make this kind of macro vegetation index and also the apparent temperature input directly. That one is much improved for the model performance. Originally, we think that the network maybe can treat all the TB to do the divider to do ratio. But if you do not input it, it's the same as it's not treated in that way. So 3 layer is enough for this kind of work.
Nice. I enjoy a lot that the time series is getting more and more dense, so you can really see nicer dry downs and so on. So that's really nice. I'm looking to that again. Anything? Is there anything on YouTube, Emanuele, that we miss?
Yes, there is just a question dealing from my YouTube. I'm trying to report this.
Yeah, I can see it already.
Just a minute, I'm reporting to the chat now. Which version of LPRM was used? Not sure that the LPRM was used in this presentation, but we please.
Yeah,
I think
I'm not confirmed. I think it's a kind of how to say public version. I will check out. I will check. I cannot remember now. I will check out which version LPRM. Yeah.
I remember there was a comparison against Chuck's LPRM in one of the time graphs, and just report which were available. Fantastic. Thanks to the question to Robin von der Charlie. Thanks for reporting it, Emanuele. I think we continue with the next presentation, which is from Cristina Vitucci, and she will talk about links between SMOS, L-band vegetation optical depths over tropical forests and ecosystem functional properties. Cristina, the floor is yours.
Yes, good afternoon. I'm sharing my screen. Okay, do you see my screen? Do you see my screen? Okay. Good afternoon, everybody. I'm Cristina Vitucci from Vergara University, and my presentation today is about the potential role of SMOS LVOD in monitoring key ecosystem processes over tropical forests. This study reveals crucial in the context of climate change scenarios. And in this presentation, I have resumed what were the fundamental steps of our study. And firstly, we investigated the relationship between SMOS vegetation optical depth retrieved using the version 650 of level 2 retrieval algorithm with above-ground biomass database coming from Habitable. The areas of study were the whole continents, Africa and South America. We have then exploited the ecoregion aggregation by Olson for both the continents, and we extracted the scatter plots between LVOD and AGB. We have then studied the spatial correlation between SMOS LVOD and ecosystem functional properties from the years 2011 to 2014, and we have extracted simple statistics. We have finally retrieved maps of predicted AFP using a random forest algorithm. We have used as a training set the whole 2011 year, and we have used as input LVOD not yearly, but monthly mean and climatic water availability layers. Firstly, for the analysis, I want to tell you something about the ecoregion units. These ecoregions are used in our study because there was useful to understand the remote sensing response in different homogeneous units. In this case, the adoption of this information layer helped us to understand better the behavior of the remote sensing information due to the lack in these continents of vegetation structure there. Respect to the classical ecoregions that comes from the application of models at global and local scale, and that considers several biophysical features. Olson uses also added information coming from species and community distribution and inputs from taxonomy, conservation biology, and ecology. Here I show you the scatter plots between SMOS LVOD and AGB. The scatter plots refers to the year 2012. the color of the scatters refers to the several ecoregions units in which both the continents appears divided using ozone classification, and it appears clear that both the graph reports two clusters, one in the lower left part and another at the bottom, at the upper right region of the scatters. At the left part, we can see small values of AGB and the corresponding small values of the small LVOD, but in Africa small LVOD present higher range, while on the right part we have the classes of Olson that corresponds to high AGB and higher values of VOD that are typical of very dense forests. The two clusters in which the scatters are divided highlights that SMOS can be a useful tool to monitor biomass at regional level. R² is quite good for both the continents. Here I reported the table that express the Pearson coefficient between small cell VOD and each AFP analyzed. It is important to spend some words about what AFPs represent. They are quantities that characterize the ecosystem processes in terms of their variations in photosynthesis, respiration, and evapotranspiration. They are precious in this analysis because they are able to detect the temporary changes of the ecosystems, give us an instant picture of what really happens in ecosystems, and it permits to optimize the uses of resources, in this case light and water. We have used, for carbon uptake, we have used in fact the Bowen ratio, that is the ratio between energy used for warming divided by the energy used for evapotranspiration, the maximum gross primary production that is related to the maximum photosynthetic capacity of the system, the light use efficiency, that is the capacity of vegetation to prevent light and to fix the carbon, the water use efficiency, that is related to the water loss by evapotranspiration in gross biomass production. We can see that each ecosystem functional properties show very high Pearson coefficient respect to LVOD for all the year analyzed, and only Bowen ratio expresses an inverse correlation. It is related to but Bowen ratio is related to the water in soil. In general, is lower in dense forest. So this is the reason why the correlation is negative. The best correlation was for GPP Max and Louis. We have here expressed the results from the scatters that reports SMOS LVOD versus Louis versus GPP Max for both the continents. Here reported for the 2014. We have similar results in Africa and South America. Each ecoregions responds with the dynamic with their dynamic according to the type of forest. For low vegetation density, we have the classes that represents dry forest at the bottom left of the graph, while in the upper part of the graph we have the classes that express that represent higher forest density and that are from moist to wet ecoregions, in which the VOD express higher dynamics. The air is good for both the continents. South America seems bit spread in terms of pixels respect to Africa. For at the end, we have used the random forest algorithm to retrieve AFP. In this case, I have reported only GPP maximum. We can see that the scatters that express GPP predicted versus the original GPP coming from AFP original data is quite good. R square is very satisfactory, and the classes are well distributed in a linear trend from the drier to the wettest. And on the left, the maps of the retrieved FP highlights latitudinal decrease of AFPs from wetter to drier ranges, which is smooth in Africa, and in South America the values are more abrupt and follows the ecoregion's boundaries. At the end, in conclusions, SMOS LBOD has the potential to estimate topical AGB and to support the monitoring of functional forest dynamics, particularly at continental scale. In specific ecoregions, SMOS LBOD and AFP tends to aggregate in clusters, and these aggregations and the relation, thanks to the relation of SMOS LBOD with AGB and FPs, we can conclude that the SMOS LBOD is also correlated with habitats homogeneity. Point is solved, and thank you.
Thank you, Christina, for the very nice presentation. So the floor is open for questions. Let's see the chat. There is, in the moment, nothing on the chat. We will have an eye on YouTube.
For the moment, we don't have anything on YouTube.
Yeah. This was just from Hui Lu's talk was there. I would have one question, Christina.
Yes.
When you use the random forest is an algorithm that needs some training and you do testing on another region. Can you explain a bit how was the training to test strategy in terms of where did you train? Or where did...
Okay, for the year 2012, I used random forest, dividing the samples that in 30% used for the training set, and the other 70% used for the validation. The scatters I show you with the reports GPP predicted respect to the GPP original from FP refers to the samples not seen by the training phase.
One add-on, maybe, or is there a question? Sorry, Emmanuel. One add-on would be
ask a question.
Oh, sure.
Yes,
Catherine.
Yeah,
go ahead.
Catherine Pridgeon. Did you filter out the surface waters in your study?
No, but I filtered using SMOS forest fraction, only pixels in which we were sure that there was forest inside, and so I think that indirectly I filtered the water.
Thanks. That's a good point.
Thank you.
Okay, I think we would need to go on to keep the time. Thanks again, Christina. And now we would move to the fourth presentation given by Fabrijean, and it's about all-weather land surface temperature retrieval from microwave observation with an improved spatial resolution. Samuel, the floor is yours. You need to unmute Samuel. You seem unmuted, but we cannot hear you. Okay.
Can you hear me now?
Perfect.
Yes, great. So can you see my screen too?
Perfect, yes.
Thank you. So I'm glad to introduce you the work we've been doing on all-weather downscaling of microwave land surface temperatures with Carlos Jimenez and Catherine Prigent. So in this presentation, I will briefly cover general information on land surface temperature, how we measure it, and how we can measure it in microwave too. And then moving on to more specifically the issue of spatial resolution and how we attempted to make progress in that regard. So introducing land surface temperature. So as you all know, it's a key parameter for numerical weather prediction, but also used in soil moisture retrievals and so on. And it's available for very few in situ stations, but mostly we use measurement from infrared sources that are really sensitive to the surface temperature. So geostationary satellites provide temperature and measurement in infrared at around 5 kilometer resolution with 50-minute revisit time. But the main issue with infrared measurement is that it's really sensitive to cloud contamination. So as you can see on the figure in the bottom of the screen, you have infrared land surface temperature with all the cloud gaps in white. Luckily, we also have a microwave that can give us information on land surface temperature. So it is available. It can use frequencies between 18 and 89 gigahertz that are available from many instruments that fly about different satellites such as SSMI or AMSR or even GMI. And is that all satellites are only polar orbiters, and due to physical constraints, the resolution reached by microwave products is only around 20-25 kilometers. So our team has been working for a while to derive a long-term time series of microwave land surface temperature using a priori emissivities and microwave brightness temperature measured by the SSMI satellite. And with this, we were able to provide a long-term series of land surface temperature. So as you can see on the bottom is from a specific area, but that compares well with other model retrievals. So now the question we asked ourselves was whether we could improve the resolution from the microwave measurement to be able to be more comparable to the one we get from infrared measurement. So this would help to complement the gaps in the infrared measurement that are due to clouds, as you can see on this figure, and also improve the usability of the microwave products. So to achieve this goal, we chose to use a statistical methodology. So this method uses low resolution temperature that come from microwave, but also high resolution temperatures that come from infrared, and also high resolution information that can come from diverse sources. So then the methodology is quite simple. We use the relationship between the information and the high resolution with the high resolution temperature to have a model that can help us derive a pattern of temperature at high resolution that can then be applied to the low resolution. Some specific adaptation needs to be done in case cloud occur, because as we'll see more about that later. So the data source we use are so land surface temperature from infrared, so at 5 kilometer resolution. Infrared derived also climatological information, so from vegetation or more information on diurnal cycle, so at the same resolution, coming also from infrared product. And for the microwave, we used the microwave series I've told you about, so from the SSMI instrument. And we also use information from model reanalysis that gives us information on atmospheric content. So coming back to the methodology, the first step is to perform a training phase using only high resolution information. So on one hand, we have the ancillary information, and on the other hand, we have the high resolution temperatures. So we combine those to get a model that can help us predict a pattern. Then with this model, we use it on each specific scene on which we want to apply the downscaling. We retrieve ancillary variables that are relevant to that scene, on which, if needed, we apply a correction for the cloud. And that gives us then a pattern of high resolution that is then combined with the microwave information, and that gives us in the end our land surface temperature at high resolution from the microwave. So the question in my ask is, how do we select this predicting information that help us derive this temperature pattern? We have knowledge of the different factors that can influence the temperature, such as vegetation on ground, and also the incoming solar radiation. And from all this, we selected a few of these predictors. So we selected the minimum of a diurnal cycle on a 10-day median. Then the amplitude of the diurnal cycle, also aggregated on a 10-day window, and also a vegetation indicator of the fractional vegetation cover. Finally, to get information on solar position, and also that gives us information on time-dependent information, we use the solar elevation. So on the left-hand figure, you see how the different combination of variables that are used as input to our model give us different error on the whole range of temperature that we encounter. And we see that only by combining these four variables, we get an error that is acceptable on the whole range of temperature. So then to get the pattern, we have, we get the pattern by combining the specific predicted temperature from a high resolution pixel with the mean of all the high resolution pixel inside one low resolution pixel. So this pattern is then combined with the low resolution temperature to get the downscale temperature. So with an example, it might become more clear. So here we created the synthetic data by averaging several observations on a 5x5 window. So that gives us roughly the low resolution that we have from microwave observation. And here we have two ancillary variables. So we use a scene here above the Okavango. So it's in the south of Africa. And that is really interesting because it has high heterogeneity because of high vegetation and changing vegetation with different seasons. So on the left, we have the minimum value of the temperatures of the diurnal cycle and the amplitude of the temperature diurnal cycle. So we see clearly the presence of water and vegetated areas near the delta that have lower amplitude but higher minimal temperature. Here we have a low resolution measurement, And then when we use that in the scheme that was described before, we get the downscale product. Here's before the smoothing step that is required, because we get this block-like artifact that are quite not really nice. And so we can then compare the downscale to the original high resolution, so in the right part of the screen, right panel, that is the original high resolution temperature measured by an infrared instrument. So we see that this method looks like it works quite well. As expected, we see in the difference that high extreme values are not as well represented as they could, but because of that is inherent to the model used. Finally, you may notice that all the data that was used in the previous steps were only available from clear sky sources. So that means infrared. So what we thought was that the temperature would be changed in the presence of clouds. So to be able to measure the impact of clouds on the land surface temperature, we used the output from the European Centre for Medium Range Weather Forecast, the ERA5 reanalysis, and used the total column liquid water as a proxy for the amount of cloud above a certain location. And on these two plots, you see with low water content and high water content, so thick clouds and thin clouds, the difference between clear sky and cloudy skies at different time of the day. So what is quite obvious is that, and as we could expect, that clouds are going to cause the temperature near the in the warmest part of the day, so around noon, are going to be colder under the clouds than when there are no clouds. So from that information, we parameterized correction on the temperature amplitude, which, as you can remember, was one of the ancillary variables that we used to correct this temperature amplitude when clouds are present. So this correction is dependent on the total column water content and also on vegetation. So with that, we have all the tools we need to provide the downscaling for all weather and any instrument in microwave. So we applied it to the SSMI instrument, and here we are for a different time. The amplitude of the general cycle and the vegetation cover over the same location, and the low resolution temperature from the SSMI instrument. When we apply the scheme, we get the downscaled product in the right panel. And if we can compare it in the clear sky part of the scene to the infrared product at around the same time. So this looks like interesting. This result is quite interesting, as we see that the spatial patterns are quite well represented that were not apparent in the low resolution scene, and also that all the cloud gaps are quite well covered because of the inherent properties of microwave remote sensing. And we also see a few apparent that makes more apparent a few issues with infrared land surface temperature that still has some cloud contamination occurring. So finally, to sum things up, we used ancillary variable from an infrared instrument to build a model to be able to downscale the microwave land surface temperature derived from the SSMI instrument. The methodology we built has around 1 Celsius root mean squared error on the synthetic data, and is applicable at all time of day. So meaning we can apply it in further step to different instruments, not only the specific time of SSMI, for instance. And also this methodology takes into account the specific impact of cloud on the land surface temperature. So now some future work is needed, of course, such as having a scheme that can be applied globally, for instance, using a polar orbiting satellite such as MODIS. And we can also, as I mentioned, use it on other microwave instruments. And finally, I'm looking forward to see how the combination of the infrared and microwave land surface temperature dataset can help us provide better land surface temperature products for the users. So thank you for your attention. And if you have any questions, feel free.
Thanks a lot, Samuel, for the very interesting talk. And the floor is open for questions. Looking for that, I don't see a lot. Looking to the. Okay, there's nothing on the YouTube so far. I would have a question, Samuel, if I may. For the cloud correction, can you specify, at least give me a number, because I'm not an expert in this field. How much cloud cover can the algorithm take on? They say, okay, if it's this and this percent of coverage, we are lost. Like where's the boundary, the limitation?
So the algorithm adapt to all cloud situations. Cloud coverage occurs like around 60% of the time around the globe. So depending on the latitude and specific location, I have more cloud cover. But when the correction we derived on the clear sky parameters is applicable to all amount of cloud covers. So usually the cloud covers is bounded, because when too much clouds are occurring, you will have usually precipitation that occurs too. So there is no unlimited cloud cover that occurs. And so we have possibly, so there is no limitation on the applicability of this correction.
Nice, thanks a lot. We have a question from Shibutsa, right? From YouTube. Thanks for posting, Emanuele. Noah Federal, how did you get the LST from the microwave brightness temperature? Sorry, I probably missed that part of the talk.
No, you didn't miss it. I think I went over it quite fast because it was not really the point of this presentation. You will find more information on the reference site at the end of the presentation, but it's basically we have an a priori emissivity and also land surface temperature, and with a neural network we can derive the land surface temperature at any time. So I'll point you the reference for more details, but
perfect. If you put it on the chat, it's awesome. So just over to my dear co-chair Leila. Would you just
thank you,
continue?
Thomas? Okay, so next contribution will be given by Francois de Montou. The title is In situ multi-frequency dielectric measurements to improve, sorry, there is some noise, to improve soil permittivity models for radiometric observations of soil in the high latitudes. Okay, please, Francois, go ahead.
Yeah, thank you. Okay, so I'm going to present you our work about the in situ multi-frequency dielectric measurements and to improve soil permittivity models, and especially in high latitude. This work involves 3 laboratories: CESBio laboratory, INRAE Institute, and IMS laboratory at Bordeaux University. This work has been carried on in the framework of SMOS mission and is supported by French CNES Institute. Previous studies have shown the impact of temperature and moisture gradient in soil top layer remote sensing monitoring, especially concerning temperature gradients in top layer. Because remote sensing signal of soil is linked to permittivity, so dielectric properties, we aim to investigate a way to obtain the permittivity profile of the soil top layer to improve the remote sensing observation of soil, especially in P and L band. So the solution we find focus on continuous in situ measurement of soil dielectric profile. So to reach this objective, we decided to develop a new instrument to make this specific measurements. indeed, some approaches has already been done using probes, TDR probe or capacity probes, to make dielectric measurement in top layer of soils. But this approach lead to coarse sampling of the profile, which is not very suitable for this study. So therefore, we work to perform and to find a new instrument and a new methodology. So we choose to select the frequency wideband electromagnetic backscattering measurements. So it consists in the use of a special antenna, and thanks to an excitation of the soil, we are able to compute the backscattering coefficient inside the top layer. So using another fast Fourier transform, we are able to compute the backscattering temporal signal, which is in fact the response of the structure to an electromagnetic pulse. And finally, data treatment permits the computation of soil dielectric profile. This is the last step we're working on, finding the right algorithm to link the backscattering coefficient to the soil dielectric profile. So let's present the instrument. So the instrument use low-cost VNI vector network analyzer connected to a specific make broadband frequency measurements and to have a low soil interaction. The VNI is also connected to a specific electronic board to command and to record the measurement. You can also save the data on memory card in case of long time measurements. And if the instrument can be connected to a network via Wi-Fi, Ethernet, and so on, we can send the data to an internet cloud. Yeah, and the instrument is specially designed so rainfall and snow are able to reach the soil and to obtain a representative in situ measurements. You can also use a solar panel or battery for autonomous measurements. Okay. Yes, we also developed a specific software. The user connected on a computer is able to download the data from the cloud. It can display the data as a function of frequency of in time domain, and is also able to compute some parameters using the first algorithm we developed. And finally, thanks to the software, you can export the data in CSV files. The instrument characteristic can be summarized in this table. So backscattering electromagnetic measurement, it's the method we choose. The frequency band for the measurement start from 100 megahertz to 3 gigahertz. Because we want this instrument to be widely deployed, we work to reduce the cost to 600 euros. So as I explained, you can record the data, you can transmit the data, you can fix the instrument on soil, and the antenna is not in the soil to avoid any perturbation. So you have main supply and so on. We add some sensor close to the antenna to be able to make measurement of temperature, humidity, or brightness. You can adjust the time steps from 1 minute to 1 hour, for example. And you have a specific data treatment software. Due to COVID travel restriction, we were unable to take measurements on frozen thawed soils. Nevertheless, we were able to take measurement on another type of soil, which with a significant permittivity gradient. It's the soil after rainfall. So here are some results of measurement we done just after rainfall. So this first result are back scattering as a function of frequency. So we can observe the good sensitivity of the instrument to the soil moisture. So as I explained, we can make a data treatment, and from a frequency curve, we can obtain the backscattering as a function of time, and so as a function of the depth. So the curves, the right curves is the curves of the radar echo as a function of soil depth, and especially we can observe the gradual increase at about 80 centimeter depth. Okay. So we can, from this data, we can obtain the backscattering at different depths and different layers as a function of observation time from 17th of April to 19th. And so we can observe the backscattering before the rainfall, during the rainfall, and after the rainfall. So in particular, we can focus on the 18 centimeter depth, where at this depth, the soil is probably more porous. So the water diffusing from the surface is concentrated at this depth, which causes an increase of the backscattering. And later, due to the hydric phenomena, water slowly diffuses in soil from this depth to the other part of the soil. So it explains the long period needed to come back to the initial backscattering value. About
sorry,
yeah,
only 1 minute left.
Yeah, okay. So, however, this graph does not allow a good observation. So we decided to merge all this data to have a more relevant representation. And on this representation, it's more easy to focus on backscattering augmentation, and also we can focus on the change of wavelengths. Wavelength is depend of the permittivity, and we can see the change of the wavelength, so the change of permittivity. We can also focus on the rainfall period, and to be able to understand exactly the diffusions of the water inside the soils. So as a conclusion, we develop a new low-cost instrument. We are able now to make a continuous in situ backscattering coefficient and to compute the backscattering profile in the soil top layer. So the next steps will be to link the backscattering coefficient profile to the dielectric profile, to make new experiments on frozen thawed soil, especially through the collaboration with CESBio in Pyrenees Mountains, and with a collaboration with Trois-Rivières and Sherbrooke University in Canada. the objective still to be able to introduce a gradient effect correction in remote sensing observation, and especially to improve the monitoring of permafrost using the L-band radiometric remote sensing observations. Thank you for your attention. If you have any question.
Thank you, François. Any question from the audience? Maybe I have a question, well, a double question, let's say. I see that you use a wide frequency range. Do you have an indication of the best frequency to make such measurements? And the second one is which kind of validation data set do you have?
Okay. Okay. Concerning the first question, concerning the frequency range, it's especially the frequency from 1 gigahertz to 3 gigahertz. The lower frequency give global information about soil profile, and higher frequency permits to have more details of the different layers in the soil. Just about top layer, if you take a look, I just make measurement on the first 50 centimeters of the top layers. So that's why this is especially the high frequency, which is useful to have this kind of detail. At 100 megahertz, sorry. At 100 megahertz, you don't have, you have a global information. And the second question concern, I don't remember. Can you repeat your question?
The validation data set, do you, which kind of measurements are you planning to use for validation?
Yeah, I am going to make simultaneous measurement using this equipment and TDR and capacitive probe. So using the probes, I will have some dielectric value over the depth, and I will try to make a relation with the interprofile I obtain with the instrument.
Okay, thank you. Maybe there is a question from the chat. No, this was for the previous presentation. Any other question? If not, we can move.
Nothing, Leila, also from YouTube.
Okay, thank you, Emanuele. First of all, I would like to ask if there is the presenter for the next contribution, Wojciech Marczewski or Jan Slominski. Are you there?
Leila, Mark just told me that possibly he appeared in the other room. Let me just try to recover him in some way. Just a minute.
Okay, thank you. Or maybe we can take advantage of these few minutes. Are there any questions for previous presentations? If someone wants to ask previous presenters, we can forward the questions to the previous presenters. Okay, no one.
Maybe I have one, Leila, because you can answer this. Christina was presenting the small cell VOD and the ecosystem functional properties. Where would you go with this study after what you showed? So you saw there's a nice correlation after the random forest with the GPP and so on. So how would this continue? What would be
okay, I'm here. Do you want to know about the recent results over this?
Yes, Christina, maybe you can.
Actually, we stopped this, but our intention is to have ground data, because the interesting parts, I think, is to have real ground data, not only. We manage data directly from the flux towers, but only a small number of data was possible to manage because the lack of the data in dense forests. So yes, the idea is to continue using ground data, but it's difficult to find. Anyway, the ecoregion characterize these areas, and sure, every remote sensing data that refers to the vegetation structure. I'm particularly working with JEDI data. I'm sure that we will find a good correlation and like SMOS data to produce a characterization of forest using an mix of to join JEDI data with these ecoregions, sure. But actually, I'm stopped with the use of ecoregion.
Well, one interesting point would be to follow the evolution in time, because the EFP changed with time, so it would be interesting to check the correlation of LVOD and EFP with time.
Temporary. Thanks a lot to you. This was an interesting insight how this could go on. Thanks.
You're welcome. Yes, Emanuele, did you find the presenter?
Yes, the presenter is in the other room. It has 2 accounts opened, but it doesn't reply to any attempt to contact him. So we tried to wrote to announce, but we didn't get any reply. So I don't know what we can do now. Possibly we can try to continue. Yes, I think
then maybe
it's preferable.
At the end we can
we will try to
resume
him. Maybe also at the end of the day, at the end of the last session, in case. But for the moment, I also tried to wrote him an email, but we not success.
Next talk will be given by the co-chair, Thomas Jagduber.
Leila,
yes?
Leila, maybe since we have a parallel session, could be better. But anyway, we are only 5 minutes in advance. Okay, no. Good, yes. Please go ahead.
Okay, yes, because I think we are a little bit late.
Okay.
Okay, so the title is Assessing Vegetation Water Potential of Winter Wheat on Field Scale by Ground-Based L-Band Radiometer. Thomas, I leave you the floor.
Thanks a lot, Leila, for the introduction. And as the talk is a bit longer, I apologize already now. I benefit from maybe having 1 or 2 minutes more. Anyhow, what we do now is we do a little excursion, because this is how with the vegetation water potential, not a, let's say, directly parameter that is directly falling out of a radiometer measurement. So what we see here is a winter wheat field, and this study is ground-based. As you can see up here, there's the radiometer, and it is for one growing season, and we like to assess the vegetation water potential. It's a study done together with Anke Flora and me from the German Aerospace, and Thomas Meyer and François Jonat from Forschungszentrum Jülich and UC Louvain, Maria Piles from University of Valencia, and from David Chaparro from Barcelona Tech. So I'll bring you now to the soil plant atmosphere system that you can see here on the left. So the soil compartment, the vegetation compartment, atmosphere compartment, and there is a water status that you can try to assess with remote sensing, and this is quite, let's say, operationally done nowadays. So for the storage parameters like soil moisture, here theta, the gravimetric moisture and vegetation, and the relative humidity of the atmosphere, we are quite good at to retrieve this with remote sensing. Then to go to the energy-based parameter, which is actually the suction tensions, let's say, or the water unsaturation in the compartments, we are not that far. I mean, more far in terms of the vapor pressure deficit, but not for the vegetation water potential and the soil mass potential. And today we will try to assess this parameter here. The vegetation water potential has like how unsaturated in terms of water is here the vegetation. And the fun part is if you can get the water potential from the atmosphere and vegetation, you can take the difference and divide it by the resistance of the flow between vegetation and atmosphere, and then you can get the transpiration. And the same can happen if you have soil moisture and then the soil matrix potential, and you take the difference between vegetation water potential and soil matrix potential, you can tell something about the plant water uptake. And this would be then dynamic parameters. This means flows per time step that you could provide to the public, which I think is also nice compared to storage parameters, which are more, let's say, static. So as I'm a remote sensing kid, I try to give you the remote sensing perspective of it. So for the water potential is a suction tension gradient. So you have negative pressures, and in the soil here, you have minus 0.2 megapascals, and in the highly unsaturated atmosphere, about minus 100 megapascals. So the atmosphere is sucking moisture out of the land surface, and this is then replenished via the soil, the roots, up the xylem, into the leaves, and then gassed out from the stomata of the leaves. What we normally observe in remote sensing is not one tree or one wheat stack. We are investigating a stand of trees or a wheat field. So we see a full biomass integral, and depending on the system what you use, and I'm here just using LBARA2 as an example, an L-band system, you might see with penetration the whole biomass integral. If you go to higher frequencies, C-band, you might see just the canopy, or if you're at X-band, you might see just the leaves. But in the end, you can have a vegetation water potential at L-band with the full biomass integral, or just the canopy potential of water at C-band, or the leaf water potential at X-band. So down the line, you see an effective vegetation water potential. So this depends on the acquisition geometry and also on wave penetration. So just to keep this in mind. Our field laboratory is at Zellhausen in Germany. This is a site run by the Forschungszentrum Jülich. And you can see here we had a bridge, and there was the radiometer LBARA2 mounted on it. It's an L-band radiometer, dual mode conical horn. And the cool thing that the guys did, they were deploying a metal mesh on ground, so any soil emission later on would be blocked by the mesh and reflected back into the soil. So anything that falls into the radiometer along the growing season would be just vegetation information. It means vegetation emission reflected by the mesh into the radiometer. And you can see we are starting at DOI 100. This is April. We're in tillering stage. This is more the grassland stage. Then we do a stem elongation. We head, and we do the heading, fruit ripening, and then we are in early senescence and late senescence here in August, day of year 225. So one growing cycle. And how you get vegetation optical depth out of this data is not, the time is not enough to explain this, and this was done already and published by a colleague here also contributing, Thomas Meyer. We start now at the soil equation. So how do we get the soil matrix potential? And we use here the soil permittivity sensors buried in 0 to 5 centimeter depth. You see this here in the blue line along the day of year. And here in gray bars, you see the precipitation daily sum. So each time a precipitation impulse comes in, you see the soil permittivity shoots up and then it dries, and next precipitation input, then it shoots up and it dries. And we're using the two in situs then to also estimate the soil-metric potential. This is model-based, so we use a model by Campbell in 1974 with parameters for soil from Klepp and Homburger. And here you see the red curve is then the suction tension in the soil, and each time, of course, as a rain comes in, the soil permittivity goes up and the suction, the tension is released. So you have lower tension, then the tension is increasing because it doesn't rain, then it rains, then the tension is released. And this way you can go along the growing period, and you see we have here in summer a drier period with less rain input, low soil permittivity, and here we go then also really down in to get to really high suction tensions, which are then released and in the end of the season in early senescence, and then we're back at the pre-level here before. Changing to the vegetation compartment, so VOD of Elben was derived by Thomas Meyer, and then we decomposed the VOD in its biomass and in its water component, and we're just showing here the gravimetric vegetation water component, which is the kilogram water by kilogram wet biomass. And you see here in gray crosses, this is the in situ measurements destructively done on the field. And with these rings, you have blue and red. This is the remote sensing estimate. And you see that we can nicely track the dry down. We're not perfect. We see in the beginning and in the end of the growing period, something goes wrong in this decomposition approach. It's the vegetation volume fraction, and we keep this constant along the time. And you can imagine vegetation volume fraction is different in the beginning of the season with low biomass on the wheat, and here in the end with maturity of with the mature stand level, and here with high biomass. And in the end, in senescence, also here it's very different. What a radar sees from, or what a microwave sensor sees from a dried wheat crop that is senescing. Anyway, this is still very nice to use, and meanwhile you could also publish this. So we have the gravimetric moisture content of the vegetation. Here what you see is we have to turn this into a relative index. So this is the relative water content. It's nothing else than the gravimetric water content normalized by a dry reference and by a wet reference. So we are going along season, and we have a wet reference here in day 135 and a dry reference here during senescence in day 220, which is really nice because here this should be really the minimum of moisture. And this is then our relative water content along the season. We want to stress, if you try to do it in an easy case and say, okay, I just take VOD and do a normalization to get the relative water content, this doesn't work in biomass dynamic environments like agricultural crops, because what you can see here, this ramp up is not moisture increase alone. This is also the biomass increase and the LAI increase and so on. So we recommend to decompose VOD and use the moisture part of it for calculating the relative water content. In plant ecology, there are several functions how you can relate relative water content to vegetation water potential. And we use here a function from Schweifer et al., published in 2001, sorry. What you see here is the function. It goes in the relative water content, then parameter K1, which is the inflection point here of the sigmoidal curves, and a parameter K2, which is the rate of change. And as we didn't measure this relationship in situ, it's not really easy to measure that, especially on a stand level. Normally it's done in laboratories on leaf or tissue level. We took just the range of changes that you can find in literature for wheat. So we have slow changes along water content with vegetation water potential, intermediate change, and rapid change, which is here the orange curve. And we used all of them to estimate the vegetation water potential. And we also have to set a minimum. And for the minimum vegetation water potential, we used from literature and from in situ knowledge minus 2.5 megapascals for wheat. This brings us to the main result. So what you see up here along DOI is the precipitation impulses. You see how the soil matrix is reacting on the impulses. This was the blue curve we already looked at with the zigzag pattern. And then in summer, this drier period where then the suction tensions grow higher and higher because the soil needs water. And the nice part is now the green curve, and the gray band around it is now the intermediate vegetation water potential and its minimum and maximum boundaries coming from this different kind of change curves. I showed you the slide before. So we cannot super resolute this kind of gray area. All of the resolutions in the gray area could be possible. Anyhow, more important for us is it shows what it should show, that the moment the soil is drying, with a certain time delay, also the vegetation is drying out. So also the suction tension is increasing here in the vegetation. And this is what we see, that soil goes first and the vegetation is following. And the fun part is blue is in situ, but green is L-band radiometer based. So it's remote sensing. And this could be a nice combination to assess the soil plant atmosphere system by combining in situ and remote sensing and radiometer measurements. Water potentials of soil and winter wheat were estimated on the field site in Jülich, in Sellhausen in Germany. And we did this along the growing season from April to August 2017. And we could assess different water potentials in this soil plant atmosphere system, namely the soil one and the vegetation one. And for the soil one, we used in situ measurements, and for the vegetation one, we could rely on L-band radiometer-based estimates of the gravimetric vegetation moisture content that we turned into relative water content, and relative water content we converted into wheat canopy scale vegetation water potential. And therefore, we adopted a model from plant ecology from Zweifel et al. In 2001 for wheat. The fun part of it is that retrieved water potential values from soil and wheat canopy, they follow the precipitation input, and they also follow each other, meaning the soil goes first, dries first, and then the vegetation goes after this. And they show a strong rise in negative potentials in a drier period between the day of year 160 and 180 in summer. This was a period of low rainfall, high evapotranspiration, and daily mean air temperature of 20 degrees, where there was a lot of evapotranspiration happening. Thanks a lot.
Thank you, Thomas. You are perfectly on time. Any questions for Thomas? I have one question. It's
one question too, but okay.
Oh, okay, Simonetta. Yes, go ahead, please.
Oh, okay.
Yes, hi. Just a question. You talk about the estimate of water potential, but the validation water potential, how you can manage it? Did you have ground data or?
There are two answers on this. One is, especially for this campaign, which was not designed to go that far, for this, we only wanted to go until VOD and soil moisture estimation. This was the first paper, and then we came to the idea to get the gravimetric moisture, and then we came to the idea, okay, let's even try until the potential. So I did have not measurements from gas chambers that somehow give an idea how the vegetation water potential could be assessed. So I don't have in situ validation. That's a problem. And for the future, it's planned that we do a dedicated campaign with plant ecologists that are at least able to measure these potentials and also the transpiration rates. It means the fluxes, at least for single plants. Maybe we can also upscale it to this field level. So this would be something we really want to try. But in the moment, I can just show here that this is a pathfinder, that we can arrive at that variable, and that the, let's say, functional behavior of what we combine here from in situ and remote sensing that we from that two worlds, that they are consistent. Yeah, but there is still the validation proof I cannot do with this data set, let's say like this.
Okay, thank you. We have time for some other questions. Are there any? Well, I was saying that I saw the plot with the soil metric potential. You show the blue line, which has a lot of fluctuations when the soil metric potential reaches low values. I was wondering which was the reason for those fluctuations.
I think that you go to lower to higher and higher suction temperatures. Huh? So I think all the parameterization that you do in the model, they come to more effect. And so this is why you can see a more jittering here. And I think this would even aggravate if you have even lower tensions. So you're getting, you know, the model is not perfect, so it's getting more imprecise. And this is, I think, what you see.
Mm-hmm.
So, just one additional comment, Campbell is just one model. There are several that we could use. So don't see this in kind of absolute precise values, see it more in trends, because we could also use other models to do this.
And they differ, the results differ when you use other models?
Yes, of course, because each model has different parameterizations and different input variables. You know, some have some input more knowledge about the soil hydraulic traits, some are more empirical and introduce less. And Campbell was a good trade-off from the in situ measurements that we had available that we can include in that model, but it's not a perfect one. So it's and you can see it's quite old, so it's a more standard model than something fancy.
Fine, thank you.
So welcome.
Okay, so other questions from the audience? I think there is, Emanuele, are there some questions from YouTube?
I'm just checking, but it seems that there are no question from YouTube. No, I do confirm that we don't have questions from YouTube.
Okay,
I mean,
but yes.
Maybe let me add one more thing. What we already try in the back office is really to estimate the fluxes, to go really until the end for this experiment. And the trends do not look unreasonable, but it's just the absolute values we cannot validate. As Simonetta was asking, we miss the in situ measurements for these potentials and fluxes. Okay, that's all. Thanks.
Okay, thanks to you. Okay, so we get to the last presentation, which will be given by Simone Pilia. The title is Airborne Multi-Frequency Microwave Radiometric Measurements in Synergy with Optical and SAR Data for the Retrieval or Hydrological Parameters.
Okay.
Simone?
Hi.
Yes, go
Hi
ahead.
to everyone. Could you see my screen?
Yes.
Yes, fine. Go ahead.
Okay, perfect. Hi to everyone. Good afternoon. For someone, good morning or good evening, depends by the jet. This is a presentation based on the results obtained from a project of research between our institute, IFAC, and the Italian Space Agency. In the framework of this project, funded by Italian Space with name Algorithmi, experimental activities based on airborne multi-frequency microwave radiometric measurements were carried out in agricultural area close to Florence. The aim of this project was to develop an innovative algorithm for crop classification and estimating soil moisture content, integrating active and passive microwave data. Retrieval algorithms are used on machine learning approach. IFAC has several multi-frequency microwave radiometers at L, C, X bands in dual polarization and also at Ku and Ka bands, and the radiometers at L, C, and X band have been installed on ultralight helicopters, which overthrew the area of interest close to Florence. In concomitant with the satellites Passage, Cosmoscape, and Sentinel-1. At the same time, ground data have been collected. Then, brightness temperature and polarization index for several frequencies have been averaged for each field and compared with ground measurements of soil moisture and vegetation biomass in order to check the result obtained in this campaign with the results obtained in past experiments. The objectives of this campaign are, first of all, to check the relationship between a microwave parameter and ground in the past years. Data obtained from the radiometric flights as a validator for the algorithms implemented at IFAC for the crop classification and estimating soil moisture content and vegetation biomass. Then we have in project to refurb our microwave sensor package in order to install it on drones, for example, use lighter and smaller antennas at L-band. The area of interest is an agricultural area along Elsa River, a river close to Florence, very few dozens of kilometers out of the city. And this area is characterized by large homogeneous field crops with sunflowers, sorghum, corn, beans, wheat, vineyard, pasture. At the same time, ground data was collected with the radiometric flights and satellites passage. These ground data consist in information of the soil, such as roughness and soil moisture content, and vegetation parameters, such as plant water content of the plants. The area of testing is depicted in this picture, in which we can see with different colors, with different kind of field crop. For example, with a green polygon, with a wheat crop, and with yellow, we have a field of sunflower. IFAC has several multi-frequency microwave radiometers, and radiometers at L, C, and X band have been installed on ultralight helicopters, which overflew the agricultural area. In this picture, we can see the microwave radiometers at X and C band on the picture on the right, with two circular corrugated horn as a sensors, and then have two kind of L-band antennas. One is a parabola with a feed, a disc dipole, and another is a patch antenna. Both of them are characterized in anechoic chamber. Also, this anechoic chamber is present at IFAC. So we compared the results obtained in this campaign with information extracted from PAX experiment. With the picture at the top of this slide, we can observe with the new points with red triangles, the points obtained with the Valdelsa campaign. And they are in a reasonable agreement with information extracted from past experiment, with the point in empty. But only 2 flights have been carried out so far for 2 reasons. One is that in the fall of 2019, many days were very rainy. In fact, these flights were done in the summer of 2019. And then in 2020, due to COVID pandemic. Passes before and after the rainfall events have been carried out. We can observe a determination coefficient equal to 0.55. Then also, polarization index at X band was related to the plant water content extracted from the ground measurements for all the crops. And then we can observe also in this case a reasonable agreement with the information extracted from past experiments. So in general, although the few new data have been acquired, the comparison was reasonable. Another purpose of this was using also the L-band data obtained from the radiometric flights as in order to validate the algorithms for estimating soil moisture content through the use of artificial neural network method with the aid of satellites information. These algorithms will be described in detail in next presentation by Emanuele Santi in room 1. The results obtained confirm that it could be possible using this radiometric data as a wider validation of the algorithms, the soil moisture content, instead of using the ground data. in this slide, I show you a map of soil moisture content of the area of interest along the Elsa River with different colors, different levels of soil moisture content extracted from the artificial neural network algorithms with the aid of satellites information. In this map, there isn't the information by Cosmos SkyMed, because on this date, 17th of July 2019, the days in which we have done the radiometric flights, Cosmos SkyMed didn't pass over the area. And then with the red lines, we put in the picture the path, the flight lines of airborne at L band, which have done on 17th of July, extracting the soil moisture content from the artificial neural network algorithms and by retrieval from the radiometric data. We compared the two information, obtain an index of correlation index equal to 0.66 and a root mean square error less than 5%. In conclusion, an experiment was carried out in an agricultural area close to Florence in the framework of a project funded by Italian Space Agency, which aimed to develop innovative artificial neural network algorithms to estimate soil moisture content, integrating active and passive microwave data. Our multi-frequency microwave radiometers have been installed on ultralight helicopters, which overflew the agricultural area in concomitance with satellites passage, and brightness temperature and polarization index for several frequencies have been compared with ground data. And the result showed a reasonable agreement also with the past information obtained in past experiments. Another purpose was using L-band data in order to validate an algorithm which based on artificial neural network method for estimating the soil moisture content with the aid of satellites information. The comparison was reasonable with an index of correlation equal to 0.66. The obtained result confirmed that it could be possible using the radiometric data as a wider validator for the algorithms in order to estimate the soil moisture content instead of using the ground data. Thank you for your attention.
Thanks to you, Simone. Are there questions for Simone? Yes, I have a question. It's about the slide with soil moisture retrieval. Is this concerning only bare soil, or is there vegetation on the fields?
Not only the soil, because the vegetation wasn't very tall, so was very few centimeters and high. And at the L band, the impact of this kind of agriculture was very small.
Okay, so you validated the retrieval only for person?
Yes, yes.
Okay, thank you.
Thank you.
Other questions? Emanuele, are there questions from YouTube?
No, nothing for the moment.
Okay, I think we are perfectly on time.
Yes, also a bit in advance.
A bit in advance, yeah. Yes. Well, actually, we missed one presentation, so yes, this is why. Emanuele, so it's time for coffee break, for a virtual coffee break, right?
Yes, yes. We will have 15 minutes for, let's say, coffee break, but in any case, it will be a break. And everyone is free to use these 15 minutes as he wants. And in this break, during the break, I would ask again, I apologize, I acknowledge I'm very annoying in this, but I would ask the presenter of the next session to join in this room for the usual test of audio, video, and screen sharing, just to avoid any kind of problem to ensure a smooth prosecution of the conference. Most important,
I had already tested 2 persons.
Excuse me, Giuliano.
I already tested 2 persons, so there are only few missed for the next part.
Okay. Most important, after the break at 5:15, I'm glad to invite all of you to attend the award, the Golden Florin or Fiorino d'Oro Award, that will be again there in room 1 from before 5 to 5:15. And that's all. I think I was. I believe I annoyed you sufficiently with these recommendations. So see you now with the presenters of the next session for test, and see you in more or less 15-20 minutes for the award, the Golden Flame Award, with all the rest of the attendants. Thank you, Leila. Thank you, Thomas. And thank you to all the presenter and attendees for this great, strong participation to the conference. We are recording very good numbers. We are in between 30 and 40 people on WebEx, and more or less the same on YouTube. So that's good. Thank you.
Okay, I would like to thank everybody, presenters and audience, and I would like to, I hope to meet you soon in person. Thank you again. Thank you, Thomas and Emanuele and Giuliano. Bye-bye.
Thanks
Bye.
from my side. Bye. Great. See you later.
See you later.
Bye-bye.
Bye.
I think the presenter, I already made the test for Martin Bauer and for Emanuele as well with them. For it's quite evident that it's been tested the microphone of Emanuele for the first part. And
I hope my
your microphone works very well.
My presentation will work. It will be really
Avinash
strange.
Sharma, if I can, if it's possible to try if your microphone, you can unmute yourself and try to share your screen to see if there's any problem for the presentation.
Okay, hello, can you hear me?
Good afternoon, yes.
Okay,
perfectly.
You can see me.
Yeah, just if it's possible to test your presentation, you should be received the right for sharing the screen.
1 second. Okay, share.
Yeah.
Okay.
Perfect. Thank you so much.
Okay, cool.
Yeah, great.
All right.
Thanks so much.
And then I will stop sharing.
Yeah. Then I would like to ask to Andrew Feldman if it's possible to make the same, to check if the video and the audio is okay. Hi, welcome.
Hello.
Hi. We hear very well.
Okay, good. You can hear me? All right.
Yeah, perfectly. Hear and see. Okay.
Screen.
Yeah.
Can you see the screen?
Great. Perfect. Thank you so much.
Okay, thank you.
Then I don't see Dara and Tekabi. I don't know, maybe Dara. No, I cannot see for the moment. Maybe we'll check later. And then Andreas Colliester. Yeah, hear him. If you can check. Yeah, welcome. Can see you very well.
Going. Sharing.
Yeah.
Hi, Andreas. How are you?
Going. Good. How are you? You can see my screen?
Yeah, perfect. That's fine. Thanks so much. And then the last is Ariane Dai. I don't know if I can. No, for the moment there is no. I don't know if there's anyone. I mean, I think Ariane Dai was the high spatial resolution soil moisture mapping, the last one. So maybe we'll check later during the session. For the moment, let's say 5 out of 7 has been already joined the meeting. So we'll check later if there are all of them coming back. Let's say. So the appointment is about it's in quarter of hour more or less.
Yes. We will never...
Simonetta already tested the from Simonetta, so everything should be okay.
I see Francesca now. Can you Giuliano, can you give the host right to Francesca?
Cigna, yes, sure.
Francesca Cigna, yes.
Hi, everybody. Nice to see you.
Hi.
Ciao, Francesca. Hi. Nice to see you.
Hi.
Hi. So, it's from one presenter. Okay.
So for the moment we have missing Dara.
Yeah,
and the
and Dara
but,
and Tekabi and Carted means that Ariane Dai was supposed to meet.
Yes, Ariane Dai, but she uploaded today
recently.
the very recently the presentation.
Yeah.
We
have presentation from all the presenter, but I mean
yes,
we are missing from what the presence, so no.
Ariane Dai is here, actually.
Okay.
Okay. Yeah, sure. Sorry.
Yeah, no problem.
Yeah, if you can just check, giving to you the right of presenting or sharing the screen. If you can try, if everything works well.
Yeah, absolutely. Let me try now. Sure.
We hear very well.
Let me see. Sure.
Great, perfect. We can see and hear very well.
Okay, let me just to the presentation mode and see.
Yes, try to go forward and back just to see, but it works.
Yeah, that's great. Okay, so only let's say Dara and Tekabi for the moment is not present. I hope she will join later. And let's say Dora.
He was joining in the past session, so I believe he will join also this one. Presentation has been uploaded, so
yeah. I'm just checking if there's
confident.
any. I don't know if there's some maybe some other person. I mean, I don't know if he's other person joining the presentation, but I mean, presenting. But say we can see, let's say, just after the Fiorinador and check if they've joined. If you want to share the screen of the.
Okay, just for the fourth presentation by Darren Tekabi, maybe any other of the authors is there.
Yeah, that's it. I was just checking the different.
Just Emanuele, and there is Andrew Feldman, which is the PhD student of Dara around. So he might.
Okay. So you will be presenting this work. Okay.
This I don't know, but at least he knows where Dara might be.
Yeah,
so,
I just sent an email to Dara. Okay. Yeah, this is Andrew. Yeah, I just sent an email to Dara. I'm not going to present his talk. I'm not actually familiar with what he's talking about, but I sent an email to him. So I'm sure he's around, but just want to make sure that he didn't have a time conversion problem.
Okay.
Thanks a lot.
Anyway, we will be back at 5:15, so we have still a few time for this. Thank you.
Okay.
Just
thanks.
Nothing. No, good. Okay. So we can wait 10 minutes and then start with the golden flooring.
Exactly.
Okay.
Yeah, I think also that Simonetta, we test the microphone of Simonetta before, so it's no need to test again. Okay.
No,
So,
mi sentite?
Sì, benissimo.
Sì, bene.
Okay.
So, let's have the coffee break now.
Exactly. Okay, thank you. See you in 10 minutes.
No, ora no, perché sono 10 minuti. C'è da se noi abbiamo fatto, cioè, a luglio c'era la versione del solito, sì, però non era solo che c'era
Sapete di avere i microfoni aperti, vero?
Okay. We are perfectly in time. So we can start with the Golden Florin Award. I'm glad to leave the floor to Simonetta Paloscia for introducing the award. Simonetta, the floor is yours.
Hi, everyone. Welcome to this 2020 edition of the Golden Florin Award. You see that the background of my screen is the room in the old palace in Florence where the first Golden Florin was awarded in 1995, many years ago. Okay, I will introduce shortly the award, and then I will leave the floor to Paolo Pampaloni, who is beside me. You see him, who is the chair of the Golden Florin. Okay, let me share my screen. Can you see?
For the moment, not yet. Yeah, that's okay.
Okay. You know that the Golden Florin Award is presented every second year to persons who, through their career, made outstanding contributions to research in passive micro-remote sensing. The award was established in 1995 by the Center for Micro-Remote Sensing, and now is jointly sponsored with the IEEE GRSS since 2014. So far, 12 Golden Florins have been awarded to many eminent scientists. The first two were Dick Moore and Erwin Shanda, and then Tom Maggi, Anatoly Shutko, Gianni Dauria, Marty Allikainen, Leo Tsang, Cole Swift, Westwater, David Levine, Tom Jackson, and the last was Phil Rosenkrantz. Okay, I will leave the floor to Paolo Pampaloni.
Thank you. To announce that the winner of the 2020 Golden Florin Award is Professor Niels Kuh of the National Space Institute of the Technical University of Denmark. Actually, Niels is a distinguished scientist, and the motivation for the award is the study of imaging microwave radiometers operating both from ground and the airborne platform for application to remote sensing on sea ice, sea salinity, soil moisture, ocean winds, oil spill, and the ice sheets. So a wide range of application. Actually, Niels is a leading scientist in the technology of microradiometry. And you see here some example of his important contribution, starting from two-dimensional radio interferometry and his contribution to ESMO's mission with the study of the Y-shaped configuration of the radiometer, and by measuring demonstrating the possibility of measuring the visibility sequentially using only 2 channels. Another example is radio polarimetry. It is by correlating very broadband radiometry signals to find the third and the fourth Stokes parameter, it was possible to measure the wind direction on the ocean. This is another very important application. Another example, the detection and the mitigation of radio frequency interference. Everybody is working on microwave radiometry, know the importance of this aspect because radiometry is easily strongly affected by interference. And this has been done by using a polarimetric radiometer with the addition of real-time processing system based on field programmable array. Well, a last but not least important contribution I want to notice is the authorship of the microwave radiometer system analysis and design, a book which represents a fundamental introduction to microwave radiometer system and the associated imaging geometry and the strategies. Is really a precious help for students and scientists. So this is a very short synthesis of what this school has been carried out during its long career. And this is the certificate which will be shipped after the meeting and includes the motivation already that contribution to design, development, optimal and the spaceborne microwave radiometer system sensing Earth's surface. Just a curiosity, you can note that the document has been signed by Paolo Ferrazzoli, Paolo Gamba, and myself.
3 Paulos.
3 Paulos. But actually, Paolo was an old coin of the Papal State, which was also used in Florence. And on this subject, there is an old saying which sounds like 3 Paulos make a penny. So it is rather irreverent, but it is not the case of the 3, or at least 2 persons. Okay, just to conclude, I will show in with quality the flooring which will be sent, I hope, in a few days. Congratulations to NISCU.
Okay, thank you. Am I allowed to say a few words?
No, please go ahead.
Pardon, can I say a few words?
Okay, sure.
Well, first of all, thank you, Paolo, for all the nice words. I actually started my career making radar systems to measure the ice in Greenland and Antarctica. So I spent a lot of time in Antarctica in the austral summer, 74, 75. But when I returned from that mission, my old professor gave me a report about radiometers and said to me, this is what you are going to build in the future and what you are going to do in the future, work with radiometers. because these crazy Americans had started to put up satellites with radiometers, and some of the old guys know about Simmer and systems like that. So this is something we have to work on also. And I've been very, very happy to work in this area, because I have so many good colleagues working at NASA and ESA and universities around Europe and United States. And I think we should all be very happy that we have a very friendly community. It's my impression that when we have issues, we can discuss them with each other and inspire each other. We don't try to hide what we do from each other. We actually are open and inspire each other, and that's very, very nice. And many of the colleagues that some of you are at the conference and some are not, but many of these colleagues are not only colleagues, they're actually friends of mine. And I think, I have not checked it, I think I've participated in all the MicroRad conferences, actually. I may have missed one, but I'm not sure. I hadn't had the opportunity to check it. So enjoy the conference also, everybody. It's a very nice conference for radiometer people. So thank you again.
Thank you. To you, Niels.
Thanks, Niels. Thanks very much.
Okay. Now I would like to leave the floor to Paolo Gamba, the president of GRSS, who wants to make a short announcement, I suppose.
Yes, thank you. I need also, if I could just use my slides, if you don't mind, Marco, or... Okay. I guess I could do it at some point. Let me just see for a moment that I have to... let me see. No, I have to go in and out. Sorry, that's one point. Sorry, I will be out for a moment and then we'll come back.
Okay. Shall I suggest to try to switch on all microphones and have a real applause instead of the recording now? Okay, thank you.
Mr. Niels.
Eccolo, ok.
No. Paolo, you are muted.
Prendi il microfono.
Is it okay right now?
Yeah.
Okay, sorry about that. So let me just go with this presentation, which is here. Should be able to get. So now you should see it. I'm just announcing at this point that given the fact that we had so many people here, the society, I mean, both society, the IEEE Geoscience Society and Chatham, decided that we are going to do something different here. So in addition to the Golden Florin Award, we are giving a 2020 honorary award to someone who has been actually a lot involved in this conference, in this group, from the starting. And of course, it is connected to this specific MicroRad conference. So let me announce, this is, as you see, is not signed by the three Paolo. And basically it's because it is to Paolo Pampaloni. We have this 2020 honorary award to Paolo Pampaloni for the foundation of Golden Florin Award and for his tireless dedication to the advancement of microwave radiometry. So congratulations, Paolo, for this award by the two societies. The point is that basically we cannot provide a golden flooring because, okay, that's already done. So we decided to give something else. And what could we provide? So basically, we are going to provide to Paolo this thing, which is a reproduction of one of the hexagonal tiles which are on the Campanile di Giotto, close to the Cathedral of Florence, which was, I mean, the original, which is this one, is in stone and was done by Pisano, where famous, I mean, it's a family. So this one is one of the family. I think it's Andrea Pisano this time who did it, and it represents the astronomy. It's a medieval representation of astronomy, and you see Janitus there, which is at the time they thought it was the son of Noé. It was the first astronomer, and this guy is looking at the sky, and as you see on the top of the tile, you see that looking at the sky, he sees God and all the angels. Of course, this is typical from what you have in the medieval times, but we can also borrow this idea from for us as scientists. When you look at something which apparently looks simple, you get a lot of things which are more and more complex. Like here, you see how many angels are there? It's like you look at the sky, you see many, many things. And why we are going to do that? Because Paolo started his passion in stars and radio astronomy at the beginning of his career. So we are going to provide him this reproduction of that tile, hexagonal tile, and as a recognition of his really tireless work for this community and for this specific conference. So once again, congratulations from the Remote Sensing Society, Political Science and Remote Sensing Society, and KTEM as well.
Thank you very much. Actually, was unexpected, totally unexpected. And it is an award without competition. It's not... anyway, I very much appreciate, also appreciate going back to the origin of my research, which was just in radio astronomy. At the time, radio astronomy was almost an early stage, as well as was at the beginning the remote sensing. With MicroRad sensing group in mid-70s. So thank you again. Thanks so much. Thank you everybody. Thank you for the collaboration, and thank especially to Simonetta, who shared with me everything I've done.
I like to show the real the real tile.
Okay, it's very nice. It's very nice. I'm pretty sure about that. Okay, so thank you again and congratulations. And that's it from my side.
Thank you. Thanks to all.
Okay, so go ahead, Emanuele.
Okay, so it was very nice, and in 10 minutes more or less we will restart with the two parallel session, land and the combined. In this case we will have the continuation of atmosphere and electromagnetic theorem models, respectively in room 1 and room 2. And that's all, I think. See you in 10 minutes.
Thank you. Bye-bye.
Can they ask Dara and Tekabi if possible to remain in the room 1 to check? Dara and Tekabi, can you hear me?
Yes, I can.
Okay, thanks. Can you make the test to see if the audio is okay and the video as well? Good afternoon, good evening.
Yeah, good morning. Yeah. I'll share at this moment.
Thanks. Thank you so much. Okay, that's perfect. So we see the screen.
I want to go into presentation mode, make sure.
There is no problem live. Okay. Thank you so much.
Sure.
Ti ho messo il presentatore, se vuoi, non so, condivido una slide provvisoria.
Sì, ora subito. La stavo preparando.
Tra 9 minuti, tra 10 minuti si ricomincia la sessione, la prossima sessione.
Sì, ora mi
Sei il chair, quindi la prossima sezione?
Sì.
Ok, perfetto. Tolgo il video, effetto ghost.
Certo, la Francesca, vero?
Abbiamo anche la Francesca Cigna come co-chair.
Ci sono.
C'è questo sfondo senza l'effetto piano, fa un effetto un po' ghost sul video.
Ora arrivo, datemi un secondo che arrivo. Si cerca di rimediare.
Vai.
Ok. Ci sei fatta a premiarti, te non volevi, ma ci sei fatta. Doveva essere presente anche Lisbeck, ma aveva lezione, quindi non poteva.
Paolo, sono Leila, congratulazioni. Approfitto di questo break. Mi senti?
Si sente?
No, aspetta, era mutato il telefono.
Si sente Leila, grazie mille.
Ciao, congratulazioni di nuovo. A presto, speriamo di vederci.
In Gran Canaria.
Chissà, magari. Vabbè, anche più vicino, dai.
Speriamo di potersi rivedere in persona presto, più che altro, perché
appunto, sì.
Queste clausure cominciano a diventare pesanti.
Io mi sto abituando, mi sa che alla fine non mi muoverò più.
Sì, è quello anche il brutto, perché uno poi si adagia.
Voi siete in giallo.
In giallo? Ah sì, noi siamo in giallo, e voi?
È rosso purtroppo, sì.
Voi siete in rosso.
Sì, perché c'è la sanità in crisi completa. Cioè, abbiamo come si dice, i letti d'ospedale pieni, soprattutto le terapie intensive.
Sì. Io ho saputo che la provincia di Viterbo è messa molto molto male, anzi la città di Viterbo. A Roma in confronto si sta bene.
Anzi, sembra che stia un pochino migliorando, però sai, fino a che non...
Sì, si fa la media su tutta la regione, se c'è qualcuno
sì, ma poi,
che...
sì. Perché al solito c'è meno contatti, è più rurale, insomma, ma la zona del centro-nord è messa malino, Pistoia, ospedale completamente pieno, Prato completamente pieno, stanno mandando i Covid a Firenze, insomma.
Vabbè, sono preoccupata per Natale perché c'è una mia zia che viene a trovarci sempre per Natale dalla Puglia, ma mi sa che quest'anno, poverina, 85 anni. Sì, ma lasciarla sola a 85 anni mi dispiace.
Tenerle in casa non gli fa bene, insomma.
No, infatti sì. anche questo è vero, sì. Diciamo che un po' di attività fisica giova anche alla mente. Bene, chiudiamo questa conversazione in italiano, forse sembra brutto.
Vabbè, una conversazione privata ogni tanto si può fare.
Ciao.
Ciao Leila.
Ciao.
Okay, apologize. We are still dealing with missing persons and the presentations, but I think now it's time to start the second part of the land session. And I will give the floor to my co-chair, Francesca Cigna. Francesca, please, the floor is yours.
Yes, thank you very much, Emanuele, and welcome back to everybody. So this is the second session about land. We have 7 speakers, and I'd like to remind each speaker has 15 minutes, 10 minutes for the presentation and 5 minutes for the Q&A. And we will start with Martin Bauer from the University of Cambridge in the UK. And the title of the presentation is Time Dynamic Vegetation Absorption and Scattering at L-band. So Martin, the floor is yours.
Hello everyone, I'll start sharing now. Okay, I hope you can see.
Yes, we can.
Okay, I'll go into presentation mode. Is presentation mode working? Okay, no. Okay. So, hello everyone, my name is Martin Bauer, and today I'll be speaking on time dynamic vegetation absorption and scattering at L-band. So I'd also like to acknowledge all of my co-authors that contributed to this study. So I'll start by revisiting the common tau omega model a little bit. So here we have a schematic on top. And the most important thing here about the tau omega model equation is that we have 3 unknowns. So the first unknown is the vegetation optical depth, like often denoted by tau. Then we have soil moisture, which will go into the rough surface reflectivity RP. And then we have here in red the effective scattering albedo, omega, which is the amount of energy loss due to scattering as a fraction of the total energy loss. And the important thing here, I marked in different colors, because normally in most retrieval algorithms, soil moisture and vegetation optical depth are target parameters, and omega is mostly seen as a calibration parameter and taken from either IGBP class or just seen as an ancillary variable. And in most studies, it is also assumed to be constant in time. There are few studies that explore a time dynamic scattering, for example, Vigneron et al. 2004. But although this study shows that there's some dynamics in this parameter, it concludes that it is okay to assume it as constant in time. So this study will ask 3 main questions. So are there dynamics in vegetation scattering on a global scale? And the second question is what actually causes these dynamics? And the third question, what can we learn from an estimation of these dynamics? And does it help us to improve parameterizations for current missions and maybe also future missions like SIMA? So in addition to the traditional tau omega framework, I'll also introduce a framework using relative vegetation absorption and scattering. So here the absorption coefficient kappa A and the scattering coefficient kappa S are used, and you can get them by normalizing tau, which is the integrated attenuation, by a vegetation height d, and then the partitioning into scattering and absorption happens by using either 1 minus omega or omega. And if you sum both of them, they build the extinction coefficient, which is the energy loss due to both effects per meter. And here I have an equivalent version of the tau omega equation using kappa A and kappa S and D. And in this study, we'll retrieve a time dynamic tau and a time dynamic omega, as well as this equivalent formulation, a time dynamic kappa A and a time dynamic kappa S. We do this using SMAP L-band brightness temperatures and a new vegetation height layer from ICSat2. To have a solvable system of equations, we need another input parameter, and we take soil moisture from MTTCA as an input to do that. So if we want to learn about the dynamics or that these parameters will have in a retrieval, it is insightful to look at the optimization spaces. So here in the left panel, you can see the optimization space optimizing for tau and omega. And the most important factor here is that there's an area of low misfit in blue that extends along the omega axis mostly, and especially at low tau. This is because at low tau, the brightness temperature change induced by a change in omega is very small. And the intuition behind this is that in the extreme scenario, at tau of 0, omega does not affect brightness temperatures at all, because both terms with vegetation in them will zero and fall out of the model. And as a result, if you have a scenario where one would have noise, this noise would lead to a misfit along the dimension of lowest gradient. And we can see here that this is along the omega axis mostly, and the violet small points are these noise retrievals, while the green dot is the original true retrieval. This is not the case in our alternative formulation using kappa A and kappa S. Here, the optimization space is more constrained in shape, and we assume that the dynamics will be partitioned into Ks and Ka. So here I took an extreme example of the retrieval that we carried out for a very dry pixel in the Sahel. And we can see that omega is very high, so it is between 0.2 and 0.6. And more importantly, we can see that there are strong dynamics, and we actually get highest values of omega during the dry season. So out of phase with LAI and precipitation in gray bars. So this again goes back to the optimization space, that if tau is lowest, and it is the lowest in these during dry season, you'll have the strongest dynamics of omega. So now I'd like to put this into a more global perspective. So here are different areas of interest that are all more than 100 pixels. And here it already looks slightly different. So for Sahel, we can see that the dynamics are a lot smaller now, but there's still some dynamics, and they follow the vegetation phenology. So this might be truly vegetation and changes in scattering caused by changes in vegetation structure. As soon as we increase the tau or the amount of vegetation even more, for example, in the Amazonas or Northeast India and Louisiana, we can see that the dynamics become really, really small. And in these areas, it might be justified to assume omega to be constant in time. So here are the same regions for kappa S, so our equivalent representation using the scattering coefficient. We can see that the scattering coefficient takes on different dynamics that and maximum mostly follows after the maximum of rain. So this is in line with how tau, for example, would look like. And this I'll show on the next slide. So here we have the retrieval of tau. And my main message about this slide is that if you look at the time series, they make sense. They follow after the precipitation and after modus LAI. So even when taking a time dynamic omega, we get a reasonable tau as an output. And similarly for kappa A, we can see that kappa A follows the peak of the rainy season. And all 4 time series here make sense and could be interpreted as vegetation water content as well. Okay, so now here's a map of the seasonal amplitude of omega, calculated as the difference between the 90th and the 10th percentile of the distribution per pixel. And we can see that over the whole globe, in most areas, we have a seasonal amplitude that is below 0.02, so that's relatively small. But as soon as we go into drier areas with low vegetation, for example, in Australia, we start getting a higher seasonal amplitude. Large areas here are masked. This is because we need vegetation height as an information to retrieve kappa A and kappa S. We mask out all areas where we don't have lighter vegetation height. But I think it's a very conservative guess to say that if we had retrievals in these areas, the seasonal amplitude of omega would be even higher because you would have even less vegetation. Here's the same map of seasonal amplitudes for kappa S. And we can see the dynamics for kappa S are generally smaller. Kappa S is in general 1 order of magnitude smaller, but also the patterns look different. And we don't have this trend of increasing the seasonal amplitude with decreasing vegetation. And this is a direct result of what I told when I was talking about the optimization spaces. So the optimization space of kappa A and kappa S is more constrained. And this is why we're not going to have these strong dynamics at low vegetation. Okay, so I can summarize that kappa A and kappa S as relative absorption and scattering coefficients can be used in an equivalent tau omega framework, and you can retrieve these parameters. They have a small advantage over the traditional tau and omega optimization because at low tau, the tau omega optimization space is weakly constrained, and we tend to get very strong omega dynamics. And this is not the case anymore if tau rises. So as soon as we go into areas with slightly higher tau, omega shows very little dynamics. And I think this is a good result for global missions that have their retrievals or their retrieval algorithms assume time constant omega. So over most areas, this works very well. And one suggestion, for example, for the MTDCA algorithm that actually retrieves an omega that is constant in time, but sets an upper boundary for the optimization. I think after looking at the optimization space, it is might be useful to relax these constraints on the upper limit and actually allow omega max to go into the full physical range of omega. Okay, thank you very much for listening, and I'm happy to take questions.
Thank you very much, Martin. This was very interesting talk. So I'm checking all the chat platforms to see if there are any questions for you. I cannot see any in WebEx. I can't see any in YouTube unless somebody is typing them right now. Just a reminder for all the participants, you can ask questions by raising your hand directly in WebEx and just asking questions directly with your voice, or you can type the questions in the two chat platforms. So any questions, anybody? Emanuele, can you see any?
I have one, just a very small curiosity. So, Martin, thank you for your very interesting presentation. Did you carry out this analysis for L-band, or did you also consider other frequencies, for instance, CX band and the other on the multi-frequency radiometers like MSR2 and something like this?
And so this specific study on like a dynamic omega or dynamic kappa A, I only carried out using SMAP L-band, but there is an older study where I used L, C, and X band. And the approach that I presented could also be used at C and X band.
Okay, this was the point of my question, if this approach is, I mean, from a theoretical point of view, is feasible, but which were the result, but in case, okay, thank you.
Okay.
We don't have from YouTube, nothing from YouTube, I do confirm.
Okay, perfect. So if anybody has questions for Martin, they can type the questions in the chats and we can try to catch up later with those. So I'm happy to move to the second speaker. Is Avinash Sharma from Johns Hopkins University in Baltimore, the US. And the title of the presentation is The Effect of Dew on L-band Emissions from a Corn Canopy. So Avinash, you can take the floor, share your presentation, and we are all listening to you. Thank you.
Okay, can you hear me?
Yes, and we can see your screen. Perfect.
Okay, good afternoon, everyone. My name is Avi Sharma, and I'm from the Johns Hopkins University Applied Physics Lab. And the title of the talk today is The Effect of Dew on L-band Emissions from a Corn Canopy. My co-investigators and authors in this talk are Dr. Kurum from Mississippi State University, Professor Roger Lang from the George Washington University, Michael Kosh from the USDA, and Peggy O'Neill from NASA Goddard. An outline of the talk will go into a quick motivation for why I undertook this study. I'll give some background on some of the modeling efforts that we did, show some simulation results for the dew effects on emissivity, and compare some modeled and measured data. So you started investigating the effect of dew on L-band emissions from a corn canopy, while I was analyzing some experimental data taken by NASA and GW using the ComRad truck-mounted radar radiometer system. And to the right, you see this is radar measured backscatter data for both HH and VV pull. And you see there's a difference between the AM and PM measurements. And so we were looking into reasons for this cause, and we looked at one of the potential contributors was dew. And so first thing you do is look into the published literature, and there were conflicting findings. And so just right here, there's a list of these are specific to passive measurements, but showing the effect of dew. Several researchers say that it has a negligible effect. Some say that the dew increases H-pull by emissions by up to 10K. Dr. Hornbuckle has some papers showing a decrease of the emissions, the emissivity due to the dew. So what I did was come up with a simple model to see what the effect really is, just to gain some physical insight. So a corn canopy or any can be modeled as a layer of discrete random media over a rough dielectric half space. And the random media consists of scatterers with prescribed orientation. The dielectric cylinders can be used to model the stems, and thin elliptical discs can be used to model the leaves. Now, the dew can be seen as a collection of small spherical water droplets on the leaf. And so at L-band, the approximation made is to take the equivalent volume of that water and just spread it as an equivalent thin layer over the surface area of the leaf. And doing that, you can use a thin disk and an analytical approximate approach, the thin disk approximation by Levine in 1984. The thickness of the disks you can use this because the thickness of the disks are much smaller than the disk radius. So the internal fields can be approximated by the electric field that would exist in an equivalent unbounded slab. And you do match your normal and tangential fields at the boundaries, and you can compute the scattering. Another approach could be you can use a dielectric mixing model. You replace the two disks with a single disk, having an effective dielectric constant. And of course, you can use numerical field solvers like HFSS or FIGO. So here's a plot showing a circular disk of radius 5 centimeters, thickness 2 millimeters. And you see for H pole, this purple line, and V pole, that's the prediction of the backscatter for a 40-degree incident angle. And when you include another disk on top, that's about 1 millimeter, looking at the dew, you see an increase in both H pole and V pole. So next, looking at this curve here, those are the three methods used: a numerical method, a moment solution, and the two approximate analytical measurements, the thin disk and the dielectric mixing models. So very good correlation with H pole. For V pole, you also see very good correlation, not as good, but it's pretty close. And the analytical solution is obviously a lot quicker to simulate than the numerical methods. So here is showing next, that information is used in a tau omega, a first order radiator transfer model. So you have the tau omega model, which largely ignores scattering effects. And you need to include the first order scattering effects, which will show dew does increase the scattering within the canopy. And so the first order scattering effects, some diagrams here show effects from the scattered ground emissions, scattered upward emissions from the vegetation layer, the scattered downward emissions from the vegetation layer, and the scattered reflected downward emission from the vegetation layer. So as we saw in the earlier slide, the effect of the dew caused an increase in the backscatter. So here we have, in just an equation form, the emissivity can be shown as a summation of 3 terms. What I'm calling the A0 term is the non-scattering solution. It takes into account absorption only. This is valid for low albedo scenes. Next, you have the S0 solution, which is the sum of the first 2 terms. This includes scattering. This is the tau omega model. And the complete expression is now referred to as the S1 solution, and this includes first order effects. So for a general simulation for a leaf, I showed parameters down at the bottom here. We see that the effect of increasing the thickness of the dew layer causes an increase in the attenuation. And if you look at the plot to the right, you see that the albedo increases from a low albedo scene of about 0.1 to a fairly high albedo scene of 0.48 for H-pole, and I'm giving numbers at 40 degrees, and to about 0.42 for the vertical polarization. So we see that scattering is going to be important when dew is included. So next we look at the horizontal polarization, some simulations for the emissivity. So for the A0 solution, we see that the emissivity increases. However, if you include the single scattering albedo, an opposite effect happens in the simulation. Recall that this is the S0, the second term is a subtractive term, so it decreases the emissivity. So you see this opposite effect where the emissivity decreases with increasing amounts of dew. But if you start including the first order scattering effects, it flips again, and you see that the dew causes an increase in emissivity. It's a small effect. It goes from 0.872 to 0.88 at 40 degrees. And that translates to roughly 3 to 4 Kelvin. And that kind of compares well with some of the papers by Dr. Hornbuckle. And we also see on this the slide to the right is the effect seems to be more pronounced as the incident angle increases. So next we look at the vertical polarization, the emissivity. Again, you see something similar where you see for the A0 solution, the dew increases the emissivity. If you include, and using the tau omega model, if you include the scattering, an opposite effect occurs. But if you include the first order effects, you see that there's practically no change in the emissivity for the levels of dew that were simulated. So next, we took some real field measurements for corn and soybean canopies. Just give acknowledgments to Professor Roger Lang at George Washington for all the dielectric measurements of the plants, Peggy O'Neill and Mehmet Kurum, who performed the measurements, the radiometer measurements, and Michael Kosh, who took the data on the dew. So just a quick overview, the dew is collected from sampling of various leaves at various locations in the plant. Paper towels were used to absorb the dew carefully from the leaves, and that was weighed compared to the dry weight to get the total amount of dew per the leaf. Based on that, the density of the water and the surface area of the leaf, and with some averaging, you could come up with a uniform thick layer that was used in the model. And based on the measurements, it looks like the dew at the time that we took the measurements was a roughly 0.1 millimeter thick uniform layer. Plugging that into the model for the soybean, the first thing we notice is that, as mentioned in the general case, that the dew has negligible effect in vertical polarization, but we see an increase in the emissivity. And so looking at the measured data, at 10 a.m., where the dew has pretty much died down, the emissivity measured is 0.869, and it increases to 0.88. And the model predicts 0.878 to 0.891. So a reasonable comparison, a reasonable correlation, but we don't see that for the vertical polarization. The measurements showed 0.929 to increasing to 0.945 for the early morning measurements, and the model there's a discrepancy there. Doing the same thing for the corn canopy, we see that, again, the measurement at 10 a.m. is 0.88, where the model is 0.881. And at 6 a.m., when the dew is present, there's an increase to 0.897, and the model predicts that to 0.895. What it doesn't predict is what's seen in the measurements for the vertical polarization. So there are potential reasons for this discrepancy that would warrant further investigation, whether that is at the time between early morning to going into the late morning and later afternoon, there might be changes to the internal vegetation water content, which is not taken into account. The model is only assuming that the dew exists on the leaf. Whether that is true, is there dew on the stalk that's causing this? So in conclusion, a simple dew model was developed and used in the first order radiative transfer model to determine the effect of dew on the emissivity at L-band. The model shows that dew increases the albedo, the single scattering albedo, and therefore first order effects need to be taken into account. The model predicts that the effect of dew the dew has an effect at horizontal polarization and seems to have negligible effect on vertical polarization. Comparing the measured and model data, the measured and model compared well for horizontal polarization for both those scenes, but did not for the vertical polarization. And this is, it's a complex modeling effort, and this is an approximate model. And there's other things and future work that I certainly would like to continue to get a better physical insight, because as I started off, there's the available published research, it's just not consistent. So it would be interesting to have a physical model to provide insights and to understand this topic better. Thank you for your time. And if you have any questions, I'd be happy to take them.
Thank you very much for keeping the times right. So are there any questions? I can see one. Okay, great. So Thomas is asking if, was there measurement just with the stalks, leaves off, so without the leaves?
Yeah, so everything was measured, the plant the length, the height, the diameters, the dielectric constants, the soil moisture, the surface roughness of the stalks and the leaves, even the cobs, we didn't include that. And the dew measurement was only made for the leaf.
Sorry, I have to clarify. What I meant was microwave measurement from the truck during where you stripped off the leaves and just measured the stalk, just to see how V-pole would react to that.
And typically the measurement, the samples are taken outside of the footprint. But it's not a lot of, there's not a lot of plant material is removed. Like, for example, for the dew, removing the dew from a plant doesn't change the scene that much.
Okay, thank you.
Thank you very much. So is there any other question from any other chat? Anything from YouTube?
No, Francesca, nothing from YouTube.
Okay, so if there are any other questions, we can catch up later again. So if you agree, it's time to move to the next speaker, who is my co-chair, Dr. Emanuele Santi from the Institute of Applied Physics from the National Research Council. And Emanuele will be presenting a research work on improving the SMAP soil moisture spatial resolution using SAR data and machine learning. So Emanuele, the floor is yours. You know how to use the WebEx tool, so all yours. Okay, thank you very much, Francesca, for your kind introduction. And I have to keep in mind after my many annoying recommendation to keep the schedule by myself.
also.
So, exactly.
Some introduction of this work, but I believe we all know very well that the coarse spatial resolution is the most important limitation to the potential of microwave satellite radiometers for the observation of the Earth's surface. And I also assume that most of you is somewhat engaged in merging SAR and radiometric data, try to improve this resolution to get better products in terms, for instance, for the soil moisture. So let me skip some general sentences of introduction I assume you already know very well, and focus directly on the description of this study. In this study, we evaluated the possibility of merging radiometric and SAR data through artificial neural networks for improving the soil moisture, in particular retrievals, in terms of both accuracy and spatial resolution. To achieve this result, we combined the data derived from SMAP, L-band radiometer, and from two SAR sensors, namely Sentinel-1 C-band and Cosmos Skymed X-band. And simultaneously with the satellite overpasses, we selected an area close to Florence in which we carried out some dedicated experiments that have been carried out in the framework of the algorithm project founded by Italian space agencies, and that provided the in situ soil moisture values for validating the results of our algorithms. The preliminary outcomes of this activity pointed out the possibility of obtaining soil moisture maps starting from SMAP at a resolution that can be better than 100 meters. This point has to be better assessed, but I have a slide at the end of my presentation about this. Okay, the test area. We are in central Italy and in Tuscany in particular, and we selected an agricultural area close to Florence, as said, with that is characterized by hilly landscape. It is difficult to find a not hilly landscape in Italy outside the Po Valley, actually. We focused on a period of several months from January to September 2019, and Simone Pilia, before the break, already described something, provided more details on the ground campaign we used to get in situ data for validation activity. And we considered the Earth observation data from SMAP. We considered both the soil moisture announced at 9 kilometers and the recent combined SMAP Sentinel-1 soil moisture at 3 kilometers, both derived from NSIDC. The Sentinel-1 VH images available on the area in the period from Copernicus Hub, and the Cosmos Skymed X-band SAR image or ping-pong data that have been kindly provided by the Italian Space Agency for in the framework of this study. After combining temporally and spatially all the data, all the images available, we found 37 combined acquisition from the three sensors, and we so started to implement and test the algorithm on these 37 data sets of almost simultaneous. The window was of about 1 day, more or less, between the overpass of each satellite. So moving to the algorithm, here's the general concept. Can you see my pointer on the screen?
Yes.
Okay, perfect. The first step is to do some pre-processing of the data. I assume that all the satellite data have been already calibrated, geocoded, and so on, if needed for the SAR images, for instance. The first step is to downsample the Sentinel and Cosmos Skymed data, and by low passing resampling, in order to have them on the same grid of the SMAP soil moisture data. So that means 3 or 9 kilometers, depending. We did test with both the soil moisture SMAP products. Combining degraded, downsampled base scattering and soil moisture from SMAP at the same resolution, we obtained the low resolution datasets that we used to train the network through an iterative architecture definition and training I will better describe in the next slide. Then the trained network is saved and applied to the full resolution soil Sentinel and Cosmos Skymed images. We considered the possibility of using only Sentinel and the combination, the synergy Sentinel and Cosmo. Some filtering and masking is applied. We have also some comparison with in situ soil moisture for validating the algorithm results. At the end, we get the soil moisture maps at high resolution and the output of the validation of the algorithm. This is summarizing is a completely data-driven approach based only on the Earth observation data for what refers to the implementation of the algorithms, and of course it is validated with in situ direct soil moisture measurements. Here, the iterative architecture I told in my previous slide is we implemented this based on the MATLAB neural network toolbox, and is composed by 3 nested loops in which we start from a very simple neural network architecture with a number of neurons equal to the number of inputs. And then we repeat the training between 20 or 100 times, but we can change these values, of course. And it also iterating for the 3 transfer function available. Each configuration is trained and the saved, and the results, the test result is evaluated. And at the end of this processing, we get the best neural network. That means that the one that obtained the highest correlation coefficient during the testing. The best, I mean, in terms of number of neurons and the hidden layer. And the scope of this quite complex system is to prevent both overfitting and underfittings that happens. This slide is more philosophy than retrieval, so I think I can skip it also because the time is not so much to go. And so we can move to the results of this. Is just an example of the one chosen by chance between the 37 combined SMAP, Sentinel-1 and Cosmos Skymed acquisition on the area. From the upper left, we see the sensitivity in here, the sensitivity of Sentinel scattering degraded the downsample at the SMAP resolution as a function of the soil moisture from SMAP. Here we can see the soil moisture map from the original SMAP product and the corresponding the histogram of distribution of soil moisture values. And below we can see the training result, that means the output of the training of the network. The soil moisture map at high resolution that is generated by using the data at full resolution. We have Sentinel and Cosmo both at 10 meters resolution, and the corresponding histogram. Some comments that can be considered valid also for the other images results. The correlation of Sentinel scattering to soil moisture from SMAP is in general quite lower. The average is more or less this one is around 0.4, and the maximum was 0.55 for all dates. And as expected is even lower for Cosmos Skymed that is expanded, so more affected by vegetation effects. In spite of this, the training result is quite good. The correlation is high, possibly because the neural networks are able to take advantage of the synergy of 2 frequencies and the 2 polarizations. The 2 maps, we can see that we have some quite good agreement between the patterns. Here the red dots are the points in which the in situ measurements have been carried out. There is a discrepancy here. It is the reason because I have selected this slide. And here the red dot here is exactly corresponded to the Fuseikyo town. So possibly there is some human-made interference that affected the SMAP measurements of brightness, temperature, and consequently the retrieval. we can see that moving to the histograms, that the average and the peak are more or less the same, but the distribution is smoothed in the enhanced product. However, we moved from an order of magnitude of the data from 100 to 10,000 data, so possibly also it affects the result. We can see that this map also describes very well some patterns related to the orography and the some features of the soil moisture that, of course, cannot be detectable in the original product at 3 kilometers resolution. Validation. Since we have also to deal with some possible geolocation error mismatch between the in situ probes and the acquisition of the satellite, we are discussing of 10 meters difference. We decided to select as estimate the soil moisture value closest to the in situ measurement in a 3x3 windows. So these three scatter plots represent the estimated versus target soil moisture, target from in situ in this case, the original SMAP Sentinel data, as expected, is a product at 3 kilometers, so we don't expect it fits very well the sparse punctual in situ measurements. The results obtained by the algorithm that only uses the Sentinel-1 data, and the results obtained by the combination of Sentinel and Cosmo. So we are talking about 30-meter resolution at this point. And we can see also that these points come from the same data, and that so possibly there is some issue with the Earth observation data that, of course, the result improves if we remove this data from the entire data set. But at the end, the question is what actually is the resolution? And we also attempted to apply the algorithm to SAR data degraded by improving the speckling low-pass filtering to 100 meters resolution. And we can see that the algorithm seems working better. It is just shown in the comparison. In the left plot, we have the estimated versus target soil moisture, applying the algorithm to the image at 100 meters resolution, and the same applied to the images at 30 meters resolution. So it seems from this that the algorithm works better, even better at the highest resolution than at a lower one. So this is my last slide. Some conclusion. So the study aimed at defining a method to improve soil moisture retrieval from satellite microwave acquisition. The algorithm seems effective in doing this, and the retrieval results at 30 meters were good, also better than those 100-meter resolution. The advantages were that this method is general. We tested it using SMAP, Sentinel, and Cosmo, but it is the same concept can be valid for other combination of radiometric and SAR data. And given the characteristic of neural networks, changing the inputs and the outputs, there is not a problem. It's quite straightforward. And just we have to repeat the training. That this has a computational cost that is now not an issue with the recent machine. The disadvantages at this point, the validation is still limited. We only applied to this area in Tuscany, and it should be extended maybe also at local scale, and maybe considering other in situ data sources like International Soil Moisture Network. We are still to work on the effective resolution to assess this, and the main limitation for operational purposes is the same of the SAR. The temporal frequency is linked to SAR revisiting. And but we can try to improve it by using different SAR sensors. As future activity, we also have the idea to use the disaggregated brightness from SMAP at SAR resolution as input for the standard SMAP retrieval algorithm. So if there is anyone interested in cooperating, you can contact us. Thank you. Just for acknowledgement, as said, this work was supported by the Italian Space Agency through the project Algorithmi. And that's all from my side.
Thank you, Emanuele. Perfectly on time. We have time if there is any question from any platform for Emanuele. Is there anybody willing to ask a question from the WebEx participants? Okay, there is one. So Nemesio Rodriguez says, nice talk. I missed what you are using as target soil moisture for the training.
The soil moisture for the training was the one from a SMAP product. And then we validated the algorithm by using in situ data from our measurements, from our experimental campaign. But the target, the values for training the network is the SMAP product.
Okay, thank you. I think we can move to the next one. Do you want to introduce the next speaker?
Okay, just a minute. Let me interrupt the...
Andrew, you can get ready. You can start to get ready. Okay.
Okay, I'm now changing my hat and from presenter to chair, and I am glad to announce the next speaker. And the next talk is map measurement show water movement in the soil plant continuous pulses. And presenting is Andrew Feldman from the Massachusetts Institute of Technology.
Yeah,
Andrew,
thank you.
the floor is yours.
Thank you. Yeah, can you hear me okay? See my screen?
Yes, okay.
Great, thanks.
I see and I hear you perfectly.
Great, thank you. Yeah, so good morning from a cold morning in Boston, and would have liked to be in Florence to give the talk, but alas, I'll have to go on my own time to Florence. So I'll give a talk today about using SMAP measurements and the microwave measurements in general to look at soil to plant water transfer, look a little bit more on the science application of this, and really use the fact that we have 1 to 3 day measurements at microwaves. We're insensitive to cloud cover, and we can really look at some shorter time scales and some exciting signals that we see there. And I'd like to thank my multiple co-authors that contributed to various studies in this talk. So there's 2 main motivations for giving this specific talk to this crowd. The first is really one, to understand more from the remote sensing side what this vegetation optical depth parameter that we've been talking about here, you've seen a few talks about, what it really represents as a parameter. Because if you take the time average of it, you can see on the right there that that right picture that the time average of vegetation optical depth gives us a very nice linear correlation with biomass properties like tree height and above ground biomass. So you take the time average over the year and you can tell that we have some biomass property. But we also know at seasonal scales that we have these seasonal cycles that represent a little bit of biomass and a little bit of water moving in and out of the canopy and relative water content. And it's somewhat unclear sometimes when you try and partition these, what the signal is coming from. If it's biomass and relative water content. And it's really important to figure these signals out, because this is very valuable information for ecosystem scientists, studying the biosphere. If you have measurements of relative water content, that's very useful information for them that they don't really have at the large scale. It's very difficult to measure those things at the field scale, and we can provide that from satellite data. Another motivation here in looking at shorter time scales, like we said, we get these 1 to 3 day measurements from SMAP and SMOS, and there's really a lot of nice applications that you can do and exciting applications you can do on sub-weekly timescales. One of which is this really under-studied climate change signal that we know that storms are becoming less frequent and more intense, and field scale studies show that this is a very important signal for the biosphere, that it can change carbon uptake by quite a bit. And you can already see these signals in the historical data, not just from climate projections. So looking at individual storm timescales is quite an important thing that hasn't really been investigated yet, because we don't have sub-weekly data. So we're going to do that here. So my research question is, is there a physical signal within the vegetation optical depth responses to rainfall on these shorter timescales? And then what physiological responses do these VOD, what physiological processes do these VOD processes represent here? Okay, so for for our analysis, it was fairly simple. We used the soil moisture time series as pretty much like a rain gauge to identify storms. So you can see in this plot here that the blue time series here. This is just one example pixel, but very representative one. You can see the blue time series that you get these storm events. It rains and soil moisture jumps up, and then it dries down. And we have identified a few there with the red dots. Those are basically post-storm periods where soil moisture is drying down. It just rained, and we're interested in what the green line is doing during those periods. What is the VOD response during those dry down periods? Is it increasing? Those are the responses we're interested in for this study. And so we'll use these SMAP measurements to investigate this at larger scales. And so I'm calling out here a few of those dry down periods, these post-rainfall periods, and you can see VOD increasing in some of these. And we found very consistent, and our main result really is we found these very consistent VOD increases following rainfall events, showing that the total canopy water content is increasing, especially when the surface is wetter. So that's one of the main conclusions we found, and that there was some different behavior. Then there was some drying that happened when the plant drying that happened when soil moisture was much lower. And we saw this behavior, that was just one example pixel I showed you. We saw this behavior very consistently across mostly drylands, actually, which was quite interesting. You can see that all the red colored pixels there are showing that exact behavior that I just showed you on that last slide, where plant water content is increasing following these rainfall events. And we additionally found that there was a soil moisture threshold that this happened at, that if it's too dry, actually, that this behavior no longer happened, that there was actually just all drying in both the soil and the plant. So this started to tell us that there was some really physical signal that was there that we can't really ignore. And specifically what this physical signal told us was a little bit about actually a process in drylands that had been hypothesized in the 1970s, but never really given great evidence at the field scale or larger scales for that. This hypothesis said that in drylands that plants basically wake up after it rains, they grow, and then they more or less go back to sleep after some drying, and they wait till the next rainfall event. And so there's these intermittent phenological periods where plants basically wake up when it rains and then go back to sleep. But this hadn't really been shown that well even at the field scale. And we showed this basically with microwave data. And just recently, I'm showing one study here, there have some more field studies that came out to show that, of course, there's this week-long and even 2-week-long growth periods that happen after even stronger rainfall events. And we're showing widespread behavior of that here that gave some evidence for this old hypothesis. So there's just also this lingering question as well that, is this just noise that we're seeing? We're looking at the more dangerous parts of the time series at shorter time scales and sub-weekly scales. So there's always the question, okay, what's the noise? What kind of noise is going on in this time series that would affect your results? And our main conclusion after lots of investigations and lots of different investigations into this was that these VOD increases that we saw after rainfall were not really due to any noise that we're familiar with, at least. And I'll tell you, so the physical signal that we're actually looking at here is a negative correlation between VOD and soil moisture. And actually the noise that exists mostly from the tau omega model and different retrieval techniques that you would use to retrieve vegetation optical depth and soil moisture, most of those occur in the positive direction, that VOD errors and soil moisture errors are positively correlated. So if anything, the signal that we're getting here, that we're evaluating, is actually subdued by the noise and not necessarily created from the noise, actually. So the noise is really in the opposite direction from the signal that we're looking at. And more recently, we also looked at ground measurements. We repeated this study in the Southwest United States, where we have some good carbon flux data in dryland locations from the FluxNet towers, from the FluxNet network. And it is carbon flux data. They're not directly going to be one-to-one relationship with a plant water content metric like VOD. But we see really the same signatures of responses following rainfall events in both the soil moisture and the carbon flux data pretty consistently. And I'm showing some examples on the right there, but even when you partition based on different sized rainfall events and the initial conditions of soil moisture before the rainfall events, you see the same response signatures in plant water content and carbon fluxes after these rainfall events that told us that a little bit more that these signatures we're seeing are something really physical that means something for the biosphere. And we dug a little bit deeper then in what, partitioning what physiological mechanisms are actually going on in the VOD time series. And I won't go too much into that. The biggest one to mention is that we really are seeing this growth response, and we used a daily leaf area index product from a geostationary satellite, Severi in Africa, to show that these larger pulses that we were seeing, these larger rainfall events, the VOD uptake after those rainfall events was actually really related to growth. They happened during growth time periods, and that was part of growth. Whereas some of the shorter time scale VOD increases that we saw that weren't during growth periods were actually these drought-related responses that have also been seen in the field, and we used a plant hydraulic model to investigate those, but I won't go into that much here. So in summary, we basically felt that we found a nice signal in these vegetation optical depth measurements on sub-weekly timescales that told us something about the biosphere, and pretty confident that we weren't just seeing noise. And it showed us some spatially extensive evidence for a previous hypothesis in drylands, and that signal that we were seeing had something to do with these growth responses and then even rehydration responses related to drought. So there was really some neat physical signal in here that we get from microwave measurements on these short timescales that I think is a nice new avenue of research. So thank you.
Thank you, Andrew. You have been perfectly in time. We have some time for question now.
Yeah.
We have one I just reported from the YouTube chat. Andy, do you account for L-band roughness coefficient increasing as the soil is drying out? Or do you assume that all of the change in VOD during the dry down is due to a change of plant water?
Yeah, that's an excellent question. Thanks, Victoria. Yeah, I looked at that about a year and a half ago, and I don't remember the exact results, but I parameterized. I played around with this and looked at how roughness would influence these, and it didn't have a large influence on the VOD. That it didn't take away or cause the VOD response that I saw, and I apologize that I don't remember the exact results I had, but I did look at this and convinced myself at the time that wasn't a problem. So thank you for the question.
Any other question?
Andrew, Martin Neira from ISA. Why would the errors in the soil moisture correct in a positive way to the VOD?
Yeah, that's a good question. So it's mostly due to the structure of the tau omega model, how just the mathematical formulation of the tau omega model, how it's written, that the soil moisture component and the VOD component become positively correlated if there are any errors there. That there's a, if I can go back to my, this figure on the right here is actually showing what the tau omega model looks like if in retrieval space. And you want to get right in the middle of that low error part to get your correct retrieval, but alas, there's going to be some errors, and they tend to be positively correlated. But what you can do is you use a soil moisture and a VOD from different algorithmic retrievals to try and decouple and not allow for that to happen. And that's something we've done as well. We took soil moisture from the level 3 from SMAP and then VOD from a separate algorithm, and you still get the same results.
But I would think that if the model is well built to reality, and not only taking into account the value of soil moisture, but the derivative, temporal derivative, the model would have also negative correlation as reality shows, isn't it?
As I missed the part about a negative correlation from, I'm not familiar with conditions for the, yeah, sorry, I might have misunderstood your question.
If the model were a good model with respect to reality, it will have to have a negative correlation as the real world shows, isn't it?
Oh, you're talking about the actual signal, how that signal comes out of it then. Yeah, it depends on the day-to-day. That depends on how the retrievals change day-to-day then. This is at least for a given overpass, this is how the errors come out. I think how the negative correlation would come out from reality would be how this happens over multiple days then. How this space on the right, it's like actually kind of, I think based on your question, that can actually get to be a pretty complicated answer to that question that I've thought about quite a bit. And it depends on several snapshots of the picture on the right there and how they evolve over multiple days, how you get this negative signal.
Okay, thank you. Very interesting presentation.
Okay.
Okay, let's move to the next talk. The title is NASA Soil Moisture Active Passive Mission Data Products Updates and Science and Application Highlights. Is presented by Dara Intekabi of the Massachusetts Institute of Technology Lincoln Laboratory. Dara, the floor is yours.
Thank you so much, Emmanuel, and it's good to see everyone, at least virtually. This is a presentation on the status of the SMAP satellite mission that is now still doing science data acquisition. Co-authors are Simon Yue from JPL and Peggy O'Neill, who are the project and deputy project scientist for the mission. Mark Garcia is currently the project manager, and Jared Entin at NASA is the program scientist responsible for SMAP. So we just went through our annual scheduled reprocessing of the data, if I could only spell reprocessing correctly. This is an annual event, and we revisit the algorithms. In this revisit, we actually made substantial changes that are important to report to the community. Also, another thing is that we had planned a SMAP VEX in 2019, then 2020, and now because of COVID, is going to be delayed until 2021. It's an airborne as well as a ground-based simultaneous field experiment. It was supposed to be, or it will be, in the Northeast US, upstate New York, and Western Massachusetts. So it's targeting the more dense temperate forest, and we have a leaf-off and a leaf-on intensive observing periods. Also, another event was that every 3 years after launch, all NASA missions, program of record, go through a senior review, and they get ranked, and the request for continuation is considered. So we just went through that, and we got very good reviews, and basically all our requests for continuity in the next few years were granted. A major aspect of the revisiting the algorithms during the annual scheduled reprocessing was a major change to how we calibrate the approach altogether of the level 1 brightness temperatures. And we have monthly cold skies, we have a noise diode, we have the ocean model, and all of that was revisited and reprocessed over the duration of the mission. We're getting calibration stability as revealed looking at global oceans of about 0.2 Kelvin for the 4 years. And that translates to less than 0.1% in volumetric soil moisture content. And looking at the cold sky, the absolute radiometric calibration is within 1 degree Kelvin and fairly stable. In terms of the validation against ground truth, we have about 12.5 core CalVal sites. These are sites that are quality controlled. They have multiple in situ sensors. Their sensors are calibrated in situ sensors. And the spatial upscaling is applied depending on the location. And there's another 12.5 which are sort of candidate sites. They don't quite have all the nice features mentioned in the lower right. And this is an example of one where it's actually pretty good. The Little Washita is a long-standing soil moisture monitoring site, decades. And the variations during the 4 years with the up and down due to rainstorms, as Andrew mentioned, and some seasonality, they track each other quite well. Not all sites are like this, both because of the poor performance of the algorithm, or something going on with the in situ site, like not being representative, or water bodies, or urban area. So, but this is an example of what can be, unless there's either algorithmic errors or in situ errors. It just shows the power of L-band radiometry. But averaging over all the CalVal sites and looking at 1 sigma random errors over the last 5 years, so this is all the data, not just that one example, the performance is around 0.3 to 0.4 volumetric error, which is well within the requirement of 0.04, and it's stable. Another major thing that was introduced in the last reprocessing was sort of unveiling of years of work on improving the dual channel algorithm. The baseline for SMAP is single channel V, and this is dual channel, retrieves both soil moisture and tau. This was underperforming throughout the mission, but now, as you see in the bottom, with all the improvements and revisits of how we implement the tau omega model for dual channel, we're getting comparable performance to baseline, with the difference that the tau is now retrieved rather than assigned from ancillary data. And this is an example of the performance of that dual channel algorithm. We still have problems in agricultural regions where the changes are too rapid. Also, we redid the SMAP Sentinel active-passive algorithm and brought it to a level of performance that is within the target accuracy. So this is a 3 kilometer, but low revisit, 12-day revisit over the entire globe, 6 days over Europe because of Sentinel matchups. But it is at 3 kilometer. To give you a sort of a visual of what it looks like, here's a region in Colorado. This is the South Platte River, also Interstate 76 highway runs across it. And in the blow-up, you see that for some reason, to the northwest of the highway, there's lots of irrigation sites, so land that is used for irrigation. On the right-hand side, it is no irrigation at all, so it's a short brush. From the radiometer, you do see a sort of a blob of higher soil moisture because it's seeing the whole region. But with the SMAP Sentinel 3 kilometer and the highway, you can see that the sharp contrast between the pivot irrigation regions and the non-irrigated regions are apparent. Sentinel is C-band, so we are ready to transition to NISAR L-band once that program is launched, probably in a year and a half. And that gives us more reach into where in the world we can do retrievals because of the L-band transition from C-band. So the red regions are considered beyond reach for both L-band and C-band. It's just too dense for that SAR to have any sensitivity. The green regions are regions we suspect that with C-band it's reachable. So the yellow region is added. It looks like a small percentage of the global area, but look where they're located. The transition regions, the crop regions around the world. So even though it's small, it's important. SMAPVEX 21 and why we go there, I'm going to leave this for Andreas, who's going to speak in a second. And that's the topic of his presentation. And also the senior review, we've been through it twice already. And this is our reports to them or our proposals to them. And there's science criteria, societal impact criteria, and technical and cost criteria that are used. And I believe I'm out of time, but an interesting question that, for instance, that they asked us was, what is your one most important accomplishment in the 3 years in one slide? And what we decided to include was the motivation for measuring soil moisture is to look at the partitioning of the surface evaporation fluxes. So this is evaporative fraction. What fraction of the surface available energy is used in vaporizing water? The lower the soil moisture, the less that partitioning. And these are several global climate models. And this important coupling between the water and energy balance is all over the map. So this is the statement of the problem, as you see here. So what we've done in the last few years is create that exact same graph, but with observations from SMAP on the x-axis and independent observations from stations, ground stations of evaporative fraction on the y-axis. So this is all observations, no models. And this is what happens on the right when you actually look at these models and how they couple statistically when you actually run the models in time, the climate. So everywhere from pure observational as well as model sensitivity of that important problem. There's lots of more that we included in our proposal to the senior reviews, NASA senior review of, and we created a bibliography of all the publications we could find using SMAP data. So it's about 850 so far, and it's on the SMAP webpage, and it's searchable. So in summary, we still have an issue with performance at agricultural sites. We are going to transition in the next 3 years as our priority to looking at high biomass regions, both in terms of field experiment as well as algorithm development. And also an important aspect of that is assessing what are we seeing with the vegetation optical depth and how can we assess it. Thank you.
Thank you, Dara. Thank you very much for your nice overview of SMAP activities. We have a question on the chat from Maria Pils. Thanks for this nice overview on SMAP. What could be the reason of PM retrievals being systematically more accurate than AM retrievals when compared to in situ?
Yeah, and that is counterintuitive, because you would expect that the tau omega model with a single temperature, emission temperature, would be violated at that time. But we are seeing slight better performance. It's all speculation of why. The difference is very small. And may have to do, we use for physical temperature, variables from a short-term weather forecast, and the discretization and the representation of the soil temperature may be, the weighing may be actually more accurate in the PM than the AM. But it is a curiosity, and we're not ready to say why, because we don't know.
Okay. Hey, Dara, just a comment on this. I assume you already well investigated the issue of the thermal equilibrium that can be changed in between AM and the PM overpasses. I mean, the temperature of soil and vegetation, the difference. it can affect the retrieval model, possibly.
Yeah, I mean, we do have, weather forecast models have a canopy temperature.
Yeah.
But that canopy temperature has zero heat capacity and it's highly unreliable. So I'm a little worried about using that temperature. But the soil temperature after overnight radiative cooling is much more homogeneous and in space and stable in time. So I'm a little more comfortable with that.
Yeah, okay. Okay. So we have another comment. It may be due to land surface temperature. That is exactly what we talked about now. So, okay, thank you. And we are perfectly in the schedule. We can move to the next presentation. Thank you, Dara, for your nice talk. Next presentation is SMAP validation experiment 2019-2021, SMAP X 1921, detecting soil moisture under temperate forest canopies. The presenter is Andreas Colliander from the Jet Propulsion Laboratory of the California Institute of Technology. Andreas, the floor is yours.
Thank you. All right, let me set this up here. Okay, so I'm going to talk about our ongoing field experiment in the Northeast US in temperate forests. We have a big team, and probably I'm not mentioning all people who contributed so far. It's been a great collaboration and ongoing for another year. Dara already talked about SMAP extensively. Just to recap, that SMAP is currently L-band radiometer with a conically scanning 6-meter dish covering the Earth every 2 to 3 days at about 40-kilometer resolution. The SMAP CAVAL methodology, we've divided in 5 main parts: core validation sites, sparse networks, satellite products, so other satellite products and model products, and then finally field experiments, which is going to be the topic of this presentation. Field experiments, we use them for providing more detailed estimates in the limited conditions for the algorithm improvement and validation of the products. Here's an overview of the field experiments so far, including the couple of the pre-launch experiments, 2008 and 2012. And then we did first post-launch experiments in Arizona 2015, then moved over to the agricultural areas in 2016 in Iowa and Manitoba, Canada. And now then we are addressing the forest issue with this experiment, which started 2019. And we were planning on doing it only 1 year, but because there was a SMAP outage just before the intensive observation period was about to start, we moved the IOP to 2020 and continued the station measurements, which we have there. But then this year, COVID upended those plans. So now we're planning the IOP next year, and the station measurements continue. So we'll have 3 years of station measurements there. We're also going to be doing a boreal extension next year with intensive observations there, accompanied by airplane. And Canadians, Aaron Burke from University of Guelph has been doing their in situ measurements already a couple of years. So it's going to be another site where we have about 3 years of SMAP scale in situ measurements, and then we have the intensive measurements planned next year, unless COVID again disrupts our plans. So, but hopefully we'll be able to carry it out next year. So this, as Dara mentioned, we moved to looking at these high biomass areas now in SMAP's extended mission phase. So here's a map of the retrieval domain as currently defined. So areas where the vegetation density is less than 5 kg per meter squared, the vegetation water content. So the black areas are those, and there are some other surface flags, but the vegetation here is sort of dominant spatially. We do retrieve soil moisture in the white areas, most of the white areas, but we haven't validated the product. So the aim is to validate this product as well and sort of bring them into the validated domain moving forward. Okay, so going then into the problem of measuring soil moisture in forests. So here is a photo taken at the tower in Harvard Forest, Massachusetts. So this is a temperate forest, very dense, tall trees, 20 meter or over 20 meter tall trees. Tower is about 25-30 meters tall, so we are above the canopy in the tower. And we can see that this is early spring, so we can see the forest floor clearly. So the expectation is that we can see the forest floor with the L-band radiometer if we can see it with the bare eyes. Of course, when the leaves come in, the view is blocked, but the vegetation water content of the leaves shouldn't be too much for L-band to penetrate, considering the other vegetated areas we can see here. It's just another view of the area. We can see that ground clear there. So in the experiment, we have two pixels, and one of them is fully forested, this Massachusetts area around that Harvard Forest, experimental forest. And then we have another area in New York, which is partially forested. And the idea there is that at SMAP scale, a lot of areas are actually partially forested. In the pixel, there isn't, like when you consider this kind of areas, Eastern US. So if we can validate the SMAP pixel within those areas where there is partially forested land cover, we have already, like, we can unmask sort of a lot of area, even if we still face too much problems in the fully forested area. So that's sort of the reason why we have these two experiment domains. So you can see the Harvard Forest area here in Massachusetts, basically fully forested, as much forested as you can without going to the too far away from civilization. And then New York area there, we have partially forested. So this is a vegetation water content map derived from NDVI as a background there. These are the two sites, 40 kilometers times 30 kilometers. We have over 20 stations at each, spread out the sites in order to cover the soil moisture variability spatially and to provide a reliable soil moisture estimate. Mike Kost's been responsible for deploying the temporary networks there, and we've been very successful with that approach. Quick highlight of we have also tower-based radiometer measurements ongoing there, and very interesting results coming out of that as well at a smaller scale. Nathan Holtzman and Alex Koenig, derived this VOD relationship with the leaf water potential there. Very interesting and relevant to what Andrew was talking earlier. So next year we are planning to do the PALS measurements there. PALS is a active passive L-band radiometer. We fly it on the DC-3, so we're planning to do 10 flights over each domain, which will result in 750 meter resolution for both. So we do about 10 flights in the summer. So then I'm going to move on to early results. I'm not going to go over this model in detail. This is a kind of simple model I applied here in lieu of the tau omega model, because tau omega model has the weakness of not modeling the scattering correctly. So that was one of the original assumptions in the model, that omega is assumed to be small in order that to be valid. So this is another simple model. It's if the scattering is 0 here, it will be exactly the same solution as for the tau omega model, but then for the scattering, it's handled a little bit differently here with this 2-layer approach. We have transmissivity and scattering of the layer as parameters. We can convert the transmissivity to tau obviously, and then roughness correction, I'm using the typical Chowdhury correction there, but actually just simplifying a little bit because it's just a multiplicative factor when you have constant incidence angle. So sometimes overly complicated presentation can be made it much easier to easier, more intuitive interpretation. So here are the first results from 2019 using this model. So tuning this model using the in situ measurements and SMAP brightness temperature. So we have on the left-hand side, we have the Massachusetts pixel. On the right-hand side, we have the Millbrook, the New York pixel. On top, we have the V-pole retrieval and bottom H-pole retrieval, both frequencies handled separately there. And what we see, and the red dots are AM and the black dots are PM observations. And what we see here is a satisfactory match with the model between the measured soil moisture and the predicted soil moisture or retrieved soil moisture. So showing like initial starting point for the experiment, we see that we can, we can show sensitivity to soil moisture from SMAP measurements, which is of course very encouraging and important going forward. It doesn't translate to the ability to do the global retrieval yet, but at least we can show that first step that we can do it. So here is a time series just showing that current, focusing here on the lower plots here. So this is Massachusetts. SMAP current retrieval is the gray stars, and we can see that in Massachusetts it doesn't do very well with the tuning. We can get the soil moisture trends out of that. Going to the Millbrook site, the current retrieval is doing a little bit better job, probably because of that partially unforested area, improving the sensitivity, but then the tuned parameters doing a pretty good job there, as expected based on the scatter plot. And the actual parameter values, so translated in, compared to the current single channel algorithm parameters, they are very different roughness parameter, much higher attenuation, vegetation attenuation actually much lower, and scattering higher. So those kind of very different combination of parameters which result to this result. So that gives us a lot to think about going forward in tuning the SMAP, improving SMAP retrievals. So in conclusion, so with sort of early results, we've demonstrated the sensitivity to soil moisture over those sites, which is excellent going forward. But that was a very simple study, and now we want to start working on improving the vegetation parameterization, improving the water content retrieval with the dual channel algorithm. We are planning to do leaf wetness measurements during the intensive observation periods, hopefully giving us more ground truth for that part of the retrieval. And then, of course, the high resolution airborne measurements will provide more insights. And then looking forward to also then expanding to that boreal zone. Thank you.
Okay, thank you, Andreas, for your interesting presentation. We have time for a couple of questions now. Any question? I would remember you can mute and unmute the microphone by yourself, so please feel free to ask a question directly to Andreas.
Maybe I have one. Thanks for the very nice presentation, Andreas. This is Thomas Sartor speaking. I saw that Alex Connings and her colleague, she's doing estimates of the vegetation water potential. I showed also something today. And for me, it would be interesting if you investigate further on that path, what you find out for L-band, what you exactly see in terms of vegetation water potential. Is it the one of the leaves or of the full canopy, or even also from the trunks? So just to understand in terms of penetration, what kind of effective vegetation water potential will you assess with L-band over forest? More comment.
Yeah, exactly. Yeah, no, that's a great comment. And that's what we are we are trying to expand in that direction in addition to the soil moisture validation. And we do have some tree sensors too, so measure the trunk dielectric constant at the different locations and at the tower site in order to investigate exactly these kind of things. There is this, and there are also 2 timescales. One is the diurnal cycle, and then one is the seasonal cycle. And we try to learn as much as we can during the experiment on that too. So that's definitely on our one of our things we are looking at within the resources.
Very nice, very nice. Thanks a lot.
Okay. If there are no more questions, let's move to the last presentation of this session. Title is High Spatial Resolution Soil Moisture Mapping Using L-band Radiometry Small Unmanned Aerial Systems. And the presenter is Ariane Dai from the University of Colorado. Ariane, please, the floor is yours.
Okay, thank you. Hi, everyone. This is Ariane from Center for Environmental Technology in University of Colorado Boulder. I'm going to talk about the high spatial resolution soil moisture mapping using L-band radiometer and small unmanned area systems. So today and on Tuesday, there are a lot of great presentations about the spacebound missions of the global mapping of soil moisture with spatial resolutions of a few kilometers to tens of kilometers. And meanwhile, for some applications like precision agriculture, flood runoff prediction, and some hydrological research purposes, we also need need soil moisture data with higher spatial resolution. So here I'm going to show a small unmanned area system capable lobe differencing correlation radiometer LDCR. So this slide shows the very first hardware system we built in 2015. The top 2 photos show the small unmanned area system Tempest with the integration of the radiometer, which is inside the L-plane, and the antennas, which is outside the L-plane near the tail. And we also found the motor and the motor controller produce a lot of interference and hit the, so the photo on the right show the proper shieldings for all the pulse, try to reduce the RFI from the motor and motor controller. The 2 photos on the bottom show the LDCR receiver board along with the RF amplifier and the data archive systems. The whole system is electrically powered, and the L-plane has done metallic L-frame, which is helpful to reduce the inference to the antenna performance. So in this project, we use the tau omega model to retrieve the soil moisture, which is being discussed in some presentations in this section earlier. So I want to point out the uniqueness of this algorithm is we are relating the unknown soil moisture data with all antenna temperature measurements using a big matrix based on their nonlinear relationship. Oh, sorry, I don't know, let's keep jumping, yeah. So this big matrix were determined from the antenna radiation pattern, soil texture information, vegetation, type information, and vegetation water content. So once this big matrix was determined, the soil moisture data can be optimally retrieved using a linear minimum mean error LMMSE estimation method. So here I'm going to show some field experiments we're using this first hardware system. The photos show the Google map of this mapping area. And in this mapping area, we have different kind of crop types. And also we have bare soil, grass, water, tree, and buildings, which is classified and showed in the plot in the upper right. Vegetation water content for this mapping area were calculated from the Landsat data with a spatial resolution of 30 meters. So as using the retrieval algorithm I discussed before, the soil moisture were retrieved and mapped for 3 days in 2016 on June 14, June 20, and June 23rd. So when applying this LMMSE estimation method, there's another thing we need to consider is the covariance between the soil moisture in any 2 points in this mapping area. So here, to retrieve these 3 maps, what we use is called a land section covariance function to calculate the covariance. So the land section covariance function, which means the covariance between the soil moisture at any 2 points in this mapping area, not only depends on their separation, but also depends whether these 2 points are located within the same land section. So the separation means the further these 2 points are separated from each other, the lower the covariance will be. And for the land sections, which means if these 2 points located in different land sections, their covariance is considered to be 0. So here I want to point is in these 3 maps, there's a little triangle area which is on the bottom of the map that we have no precipitation and irrigation within these 9 days. And it's noticeable that in this triangle mapping area, the soil moisture decreased significantly from June 14 to June 23rd. And also the spatial resolution of these 3 maps is 5 meters. It's approximately 5 meters by 5 meters. So this slide shows the 3 maps. We used a different kind of covariance function, which is called uniform correlation land section covariance function. That we assuming that the soil moisture within each land section has a uniform value. So you can notice that the retrieved soil moisture maps has a uniform value within each land section. This function can be helpful for the agriculture, for the precision agriculture. For example, if we want to make the irrigation plans, the average soil moisture for each land sections will be helpful if we want to determine how much water we want applied and we want to do the irrigation. For both land section covariance function and uniform correlation land section covariance function, the soil moisture are strongly correlated with the correlation coefficient equal to 0.93 for all crop types. And also the correlation coefficient is very high for each kind of crops, as shown in the plot on the right bottom. So next, I'm going to compare this retrieved soil moisture data with the in situ measurements. In this mapping area, there are 8 probes installed in different land sections, as shown in the map in the upper left. And the retrieved soil moisture are strongly correlated with the in situ measurements with correlation coefficient equal to 0.69 for all 3 days measurements. And also, we also compare the retrieved soil moisture with the irrigation records for each land section. So you can notice that for the land sections with irrigations, we notice the soil moisture increase or have pretty much the same value or decrease much less compared with other land sections with no irrigations. So which means the retrieved soil moisture also consistent with the irrigation records. So next, I'm going to show a newer hardware system we've been working on since this year. The left 2 figures show a newer design of the LDCI receiving board, which is more compatible. That we have the RF and IF circuits on the top surface, and the ADC and a microcontroller SD card on the bottom surface. And in the future, this board will be connected to a red battalion board for the future RFI mitigation purposes. And you may notice that on this board, we have two identical receiving channels. So during the calibration process, we have considered the unbalance of the gain and phase delay of these two receiving channels to get precise expression of the output voltage. The two photos on the right show the integration of the new hardware of the LDCR along with the audio camera on a newer small unmanned area system platform, Super Swift. Similar as Rev-A and Tempest, the whole system is electrically powered. And in the lab tests and some pre-flight tests, we find the RTM camera itself introduced a lot of interference to the radiometer. So we did some efforts so far, try to shielding the noise source and all the cable connections. And so far, we're still working on this, try to further reduce the noise level. So the RTM camera I mentioned before has 6 bands, including red, near infrared, and thermal infrared. So for the newer system, we don't need to download the satellite data, but instead we're going to using all the images captured by the RTM camera and then combine all the images together into one single map of NDVI data and one single map of the surface physical temperature map with the same spatial resolution as the thermistor data we want to generate. So here shows some initial maps we're using the newer system. So far, we've been validating the performance of the radiometer and the RTM camera separately. The radiometer was flight in April the 1st over this area in Salt Farm in Colorado. And you can notice the map of the brightness temperature has a region with very low brightness temperature compared with the other areas, and the boundary consistent with the boundary of the Google map that we have the waters. And later in May the 15th, the performance of the RTM camera is being validated too. And the NDVI data and the TP maps were generated based on the RTM images. And similarly, you can notice that the NDVI data and the surface physical temperature maps the boundaries on the Google Maps too. That in the pound, we have the NDVI data lower than 0. And in the bare soil on the bottom of the pound, the NDVI is almost 0. And on the upper side of the pound, that where we have the vegetation covers, the NDVI data is higher. And similarly, for the TP maps, and we notice the bare soil has a higher surface physical temperature compared with the pound area and the vegetation areas. So summary, so far we built a small unmanned area system based L-band radiometer for the high spatial resolution mapping. And the performance of the hardware system and the algorithm has been validated during some field experiments. That the retrieved soil moisture has good consistency with the in situ measurements and the irrigation records. And the latest hardware system is being developed that we will have both radiometer and RTM camera, which will be capable to map the high spatial resolution soil moisture data, NDVI data, surface physical temperature, and the brightness temperature data. So that's my presentation. Thank you for your attention.
Thank you, Ariane, for your nice work. We have time for a couple of questions. No questions from the audience on chat? No. So it means that you have been very clear in your presentation, and now all is clear for this work. Thank you. Thank you again. And this concludes, I would say, we are perfectly in time. This concludes the session, and all the session of this day in room 1. I would warmly thank all the presenters, the attendees, and the people supporting in this activity, and all of you at the end, and see you tomorrow. Let me just recall very quickly the program for tomorrow. Tomorrow is the last day of MicroRad 2020, and we will return back to single session, and we will have all the day dedicated to sensor. At 2 o'clock, we will have the last keynote, and then at 2:30, of course, PM and Central Europe time, till 4:30, we will have the first part of sensor session. Then we will have the usual 30 minutes break, and then the second part of the sensor session till 6:30 p.m. and then the farewell, and that's all. And see you tomorrow. Thank you again to all of you.
Thank you.
I would also, this is the most important, I'm going to forget it, but it was very helpful to thank my co-chair Francesca for, she helped a lot me in training this session. Thank you.
A pleasure. Thank you for chairing and organizing the session. Thank you, Emanuele, and see you to everybody. Bye.
Bye.